Imagine a universe so vast it holds more stars than there are grains of sand on every beach on Earth combined. This unimaginable scale beckons us to embark on an exhilarating journey, guiding us through the wonders of our solar system while unveiling the enigmatic forces that shape the cosmos. From the majestic rings of Saturn to the violent, swirling storms of Jupiter, each celestial body in this universe guards secrets just waiting to be unlocked. The universe teems with mysteries that challenge our understanding and invite us to delve deeper into the fundamental workings of existence itself. We begin our journey by exploring the awe-inspiring origins of our solar system. This captivating tale stretches back about 4.6 billion years, when a massive cloud of gas and dust, known as the solar nebula, began to collapse under its own gravity. As this colossal cloud compressed, it began to spin rapidly, forming a flat, rotating disk. Within this spinning disk, solid particles stuck together, gradually growing larger and coalescing into bodies called planetesimals. Over time, these planetesimals collided and merged, eventually leading to the formation of the planets and other celestial bodies that populate our solar system today. But this is just the beginning of the mysteries that surround planetary formation. One of the most fascinating puzzles is why the inner part of the solar system gave birth to rocky planets like Earth and Mars, while the outer regions became home to gas giants such as Jupiter and Saturn. Scientists speculate that the key to this division lies in the temperature gradient that existed within the solar nebula. Closer to the Sun, where temperatures were higher, only metals and rocks could condense, leading to the formation of terrestrial planets. Farther out, in the colder reaches of the solar system, lighter materials like hydrogen and helium remained, enabling the birth of massive gas giants. Another profound question revolves around the presence of water, an essential ingredient for life. How did this vital substance find its way into the inner solar system? Some researchers propose that comets and asteroids, remnants of the early solar system, delivered water to Earth through catastrophic impacts. Others suggest that chemical reactions within the solar nebula itself may have played a role in introducing water into our planet's environment. This debate highlights the complexity of our solar system's origins and raises fascinating questions about how life began on Earth. Then there is the mystery surrounding the strange orbits of some comets and asteroids. Many of these objects follow irregular, erratic paths that seem to defy the orderly arrangement we see with the planets. What causes this? Could it be the gravitational influence of larger bodies, or perhaps even the presence of unknown clusters of matter lurking beyond the known planets? This uncertainty opens up new avenues for investigation and further deepens our understanding of our solar system's past and its future. As our exploration continues, we turn our attention to the rapidly evolving field of exoplanet discovery. Over the past few decades, astronomers have employed increasingly sophisticated methods to identify planets orbiting stars far beyond our solar system. Two primary techniques dominate this effort: the transit method and the radial velocity method. The transit method involves carefully monitoring the brightness of stars. When a planet passes in front of its host star, it blocks a fraction of the star's light, causing a slight but detectable dip in the star's brightness. This momentary dimming not only reveals the planet's presence, but also offers vital information about its size and orbital period. Space telescopes like Kepler and TESS have revolutionized this technique, identifying thousands of exoplanets by observing the subtle changes in light from distant stars over time. In contrast, the radial velocity method relies on detecting the minute wobble of a star caused by the gravitational tug of an orbiting planet. As the planet exerts its gravitational force, the star shifts ever so slightly, leading to observable shifts in the star's light spectrum, a phenomenon known as the Doppler effect. This technique has proven invaluable in confirming the existence of many exoplanets, particularly those that are too small to cause significant dips in their star's light. Once an exoplanet is identified, scientists take it a step further by analyzing the light that passes through its atmosphere during a transit. This allows researchers to identify various gases present in the planet's atmosphere, which can offer clues about its potential habitability. Thanks to ever-advancing telescope technology and observational techniques, exoplanet research continues to expand rapidly, providing us with unprecedented insights into these distant worlds and their potential to harbor life. Among the most intriguing bodies in our solar system is Titan, Saturn's largest moon, which has become a key candidate in the search for life beyond Earth. Titan's thick, nitrogen-rich atmosphere bears a striking resemblance to Earth's, providing a potential environment where life could emerge. The moon's dense atmosphere facilitates complex organic chemistry, offering clues that suggest Titan could harbor essential compounds needed for life as we know it. Beneath its thick cloud cover, Titan's surface is dotted with lakes and rivers filled not with water, but with liquid methane and ethane. While these hydrocarbons differ from the water we rely on for life, their presence hints at an alternate form of chemistry, one that could support life in Titan's harsh, cold environment. With surface temperatures hovering around minus 290 degrees Fahrenheit, water is too unstable to exist in liquid form. Instead, these extreme conditions create an environment where entirely unique chemical processes might occur. Some scientists speculate that microbial life could exist in these frigid, methane-rich conditions, challenging our preconceived notions about where life can thrive. As we look deeper into the cosmos, we uncover a universe teeming with unimaginable complexities, each discovery pushing the boundaries of our knowledge and challenging our very understanding of what is possible. From the birth of planets to the possibility of life in the most extreme environments, the journey to understand our solar system, our galaxy, and the vast universe beyond promises to be one of the most profound and exhilarating undertakings in human history. Moreover, scientists have long speculated about the possibility of a hidden ocean beneath Titan's icy surface. This ocean, believed to be composed of salty water, could provide the perfect environment for life, mirroring the diverse ecosystems found in Earth's oceans. The idea that a similar world exists beneath Titan's crust presents an exciting frontier in the search for extraterrestrial life. Titan, Saturn's largest moon, holds the promise of harboring life forms uniquely adapted to the harsh, frigid conditions that prevail there. These organisms, if they exist, would challenge our very conceptions of life, showing us that life could thrive in places previously thought inhospitable. In recent years, our ability to study Titan has grown significantly, thanks to missions like the Cassini spacecraft, which studied Saturn and its moons for over 13 years. Additionally, the upcoming Dragonfly mission set to launch in the coming years will delve even deeper into Titan's mysteries. Dragonfly will explore Titan's surface, analyzing its organic materials and potential for life directly. What makes Titan so intriguing to researchers is not just its thick atmosphere or its complex organic chemistry, but the possibility of liquid water hidden beneath its icy exterior. These factors combine to create a dynamic environment that might just be the key to unlocking the mystery of life beyond Earth. Titan's dense atmosphere is an essential feature in this equation, as it has likely played a significant role in shaping the moon's chemical environment. The presence of methane, ethane, and other organic compounds in Titan's thick clouds suggests that complex organic chemistry is taking place, offering a kind of cosmic laboratory for researchers. Beneath this haze, Titan's subsurface ocean could provide a liquid water reservoir, crucial for sustaining life. These elements, when combined, make Titan one of the most promising places in our solar system to look for extraterrestrial life, pushing the boundaries of what we thought possible in the search for life beyond our planet. Meanwhile, Titan's icy cousin, Enceladus, another one of Saturn's moons, has astonished scientists with its geysers, which expel water vapor and ice particles into space. These plumes, first discovered by the Cassini spacecraft, are not just visually stunning. They hold critical information about the possibility of life beyond Earth. Enceladus presents a compelling case for life in environments vastly different from Earth's. While most of our assumptions about life have centered on warm, sunlit environments rich in liquid water, Enceladus turns that assumption on its head. Despite its frozen exterior, Enceladus hides a subsurface ocean kept warm by the gravitational interactions with Saturn. This heat is produced by tidal forces that create geologic activity beneath the surface, potentially providing the right conditions for microbial life to flourish. The geysers themselves are a window into this hidden ocean. When they erupt, they release material from beneath the ice, including organic compounds, essential building blocks for life. This discovery has sparked new debates in the scientific community about the conditions necessary for life. Enceladus challenges the notion that life can only exist in Earth-like conditions, and it opens up the exciting possibility that life could exist in environments previously thought to be uninhabitable. By studying the plumes, scientists are not only searching for signs of microbial life, but also trying to understand the complex chemistry that could emerge under extreme conditions. This shift in perspective invites researchers to expand their focus to other ocean worlds in the solar system, exploring regions that were once dismissed as uninhabitable. Europa, one of Jupiter's most fascinating moons, is another such ocean world that beckons researchers. The surface of Europa is an enigma, completely covered in ice, yet scientists believe it hides an ocean beneath. This vast salty ocean, sealed beneath the icy crust, is thought to be in contact with Europa's rocky mantle, creating the potential for a chemically rich environment. These interactions could mirror the conditions found around hydrothermal vents on Earth, where life thrives despite the absence of sunlight. Europa's ocean is believed to contain more than twice the amount of water found on Earth, suggesting that this moon could harbor a thriving ecosystem, possibly even microbial life within its depths. In addition to the ocean beneath its icy surface, Europa's fractured, ridged ice shell suggests significant tectonic activity. This movement could allow nutrients and energy from the ocean below to reach the surface, further supporting the idea that the moon's environment could be conducive to life. Scientists have also detected regular plumes of water vapor erupting from the surface, hinting at a dynamic exchange between the ocean and the outer environment. These plumes could provide a unique opportunity for studying Europa's ocean without the need for drilling through the thick ice. Missions like the European Space Agency's Jupiter Icy Moons Explorer, JUICE, and NASA's Europa Clipper are set to explore Europa in greater detail, aiming to unlock the mysteries of its ocean, its chemistry, and its potential to support life. With each new finding, Europa stands out as one of the most promising places in our solar system to search for extraterrestrial life. Closer to home, Mars has long been regarded as Earth's closest neighbor and a prime candidate in the search for life beyond our planet. Observations of the Martian landscape reveal a planet once shaped by a dynamic history, marked by changes in climate and environment that offer vital clues about its potential to support life. Recent missions have uncovered evidence suggesting that liquid water once flowed freely on Mars. Images of ancient riverbeds, lake beds, and minerals that form only in the presence of water tell the story of a planet that may have once harbored life. Water is a fundamental ingredient for life, as we understand it, and the discovery of ancient water on Mars has ignited new excitement about the possibility that microbial life may have existed there in the past, or could even still exist today in some form. This evidence paints a picture of a world that was once warm and wet, with conditions that might have supported life. As we continue to explore Mars, we move closer to answering one of humanity's most profound questions. Could life have existed beyond Earth, and might it still? With each new discovery, from the icy moons of Saturn to the red sands of Mars, the boundaries of habitability are expanding, and the quest for life beyond Earth continues. As scientists push the limits of exploration, they are not just searching for life, they are reshaping our understanding of life itself. The current state of Mars stands in stark contrast to its ancient past. Today, the planet is a cold, arid world, with a thin atmosphere dominated by carbon dioxide. Yet, this wasn't always the case. By understanding the mechanisms that led to such a dramatic transformation, scientists can better understand how planetary environments evolve over time. These shifts are more than just historical. They hold critical implications for the potential emergence of life, the resilience of any life forms, and their ability to survive harsh conditions. The timeline of when life might have first emerged on Mars is intricately tied to these changes. By examining the planet's past, we can gain insights into how it may have once supported life and the conditions necessary for its survival. These insights are not only vital for understanding Mars' history, but are also key to planning future human missions to the Red Planet. Studying how Mars has evolved over millions of years gives us the tools to assess where microbial life might still exist today. The remnants of ancient water, along with geological features that hint at past liquid water, guide researchers in piecing together the history of the planet's climate and surface. The exploration of these features sets the foundation for humanity's bold journey to Mars, where we hope to unlock the secrets of life. Whether microbial or otherwise, life on Mars could redefine our understanding of biology, evolution, and the very nature of existence in the universe. Meanwhile, Venus, often referred to as Earth's twin due to its similar size and proximity, harbors a world of hidden potential beneath its seemingly inhospitable surface. With surface temperatures averaging around 450 degrees Celsius and an atmosphere predominantly composed of carbon dioxide, Venus presents extreme conditions that challenge our understanding of what makes a planet habitable. Yet beneath this harsh exterior, there may be secrets waiting to be uncovered. Scientists are particularly intrigued by the possibility of a more temperate environment within Venus's upper atmosphere, roughly 50 kilometers above the surface. Here, the temperature is surprisingly mild, hovering around 20 degrees Celsius, offering a stark contrast to the inferno below. This temperate zone is a subject of growing interest, as it might offer a refuge for life, or at least the conditions necessary for microbial organisms to exist. Additionally, Venus is rich in valuable materials that could prove essential for future space exploration and resource exploitation. Volcanic plains and mountainous regions hide vast deposits that could play a key role in advancing space missions or even fuel mining operations in the future. As we expand further into our solar system, the geothermal activity that shapes Venus's surface offers valuable insights into planetary geology, like lessons that could inform our understanding of other worlds. Venus also provides a unique laboratory for studying climate change. The planet's runaway greenhouse effect, which has transformed it into an inhospitable world, raises important questions about Earth's own climate future. By examining Venus's climatic history, scientists can gain essential insights into how Earth's climate might evolve and what steps we might take to mitigate the risks of a similar fate. Thus, while Venus's hostile surface might make it seem like an unwelcoming world, its potential to provide groundbreaking scientific knowledge is immense, and it stands as a treasure trove of opportunities waiting to be explored. At the heart of planetary habitability is the role of magnetic fields. A planet's magnetic field plays a crucial role in protecting its atmosphere from the relentless barrage of solar wind. Solar winds, streams of charged particles emitted by the sun, can strip away a planet's atmosphere over time, leaving it vulnerable and unable to retain the conditions necessary for life. The magnetic field acts as a shield, deflecting these particles and preserving the integrity of the atmosphere. Earth, with its robust magnetic field, benefits from this protection. The magnetic field deflects solar winds, ensuring the stability of our atmosphere, which in turn helps sustain life by keeping liquid water on the surface, a fundamental ingredient for life as we know it. Without this protection, Earth would be more like Mars, cold, dry, and barren. In contrast, Mars, with its weak magnetic field, has suffered significant atmospheric erosion over billions of years. This loss of atmosphere has led to the cold, dry conditions we observe today, making it nearly impossible for life as we understand it to survive. Magnetic fields also play a subtle but significant role in maintaining the chemical balance of a planet's atmosphere. They help prevent charged particles from triggering harmful chemical reactions, preserving essential gases like oxygen and carbon dioxide. The stability of these gases is critical for sustaining life, as they play key roles in processes like respiration and photosynthesis. Without a protective magnetic field, a planet's atmosphere would likely degrade, and the delicate balance needed for life would be lost. As we continue to explore other planets and search for extraterrestrial life, understanding the role of magnetic fields becomes increasingly important. It is not just the ability to protect the atmosphere that matters, but also the preservation of the planet's atmospheric composition. The interplay of these factors is central to the emergence and persistence of life. One of the most fascinating and least understood regions in our solar system is the Kuiper Belt. Stretching from the orbit of Neptune to about 50 astronomical units from the Sun, This vast region is populated by small icy bodies, remnants from the early solar system. Studying the Kuiper Belt helps scientists piece together the history and formation of our solar system, revealing the processes that shape the planets we know today. The belt contains a variety of objects, including dwarf planets like Pluto, along with many smaller bodies. These celestial objects serve as ancient time capsules, holding clues about the early solar system. Their composition and orbits reveal much about the conditions that existed during the solar system's formation, offering valuable insight into the materials that were present at the beginning of our cosmic neighborhood. As scientists continue to study these distant bodies, they are learning more about the solar system's early days and how these ancient remnants have remained relatively unchanged for billions of years. These frozen objects are like windows into the past, holding secrets about the origins of our solar system and the processes that have shaped the planets, moons, and comets that populate it today. Understanding the Kuiper Belt not only helps us grasp the history of our own solar system, but may also offer insights into other planetary systems and their formation, deepening our understanding of the universe as a whole. Moreover, the Kuiper Belt marks a critical boundary between our solar system and the vast expanse of interstellar space. It's often considered a source of numerous short-period comets, which originate from various regions within the belt. These comets, as they journey toward the inner solar system, offer us a glimpse into the primordial materials that may have played a pivotal role in the origins of life on Earth. As our exploration of the outer solar system progresses, especially through groundbreaking missions like New Horizons, which made its historic flyby of Pluto, our understanding of the Kuiper Belt continues to grow deeper. Each new discovery challenges our previous assumptions, shedding light on the complexity and dynamism of this distant region. Far from being a mere boundary, the Kuiper Belt reveals itself to be a bustling and scientifically rich environment that defies the traditional view of our solar system's edge. This dynamic outer solar system has proven to be far more than we initially imagined, holding countless secrets that speak to the evolution of our planetary neighborhood. In a vastly different realm of the universe, a black hole stands as one of the most enigmatic objects known to science. With an incredibly strong gravitational pull, a black hole exerts such immense force that not even light can escape its grasp. This strange phenomenon is born when a massive star exhausts its nuclear fuel and collapses under the weight of its own gravity. What results is a region of space where gravitational forces dominate completely, creating what is known as the event horizon, the boundary beyond which nothing, not even light, can return. However, detecting such an elusive object, one that emits no light, is a considerable challenge for astronomers. Yet, they have developed ingenious methods to infer the presence of black holes. By observing the impact a black hole has on its surrounding environment, scientists can piece together the nature of these invisible giants. When a black hole pulls in gas and dust from a nearby star or from the interstellar medium, it forms an accretion disk, a spinning, heated mass of material. As this material spirals inward, it emits powerful radiation, particularly in the X-ray spectrum, allowing astronomers to detect the black hole's activity through specialized telescopes. Another method for observing black holes involves the detection of gravitational waves. These ripples in space-time, created by catastrophic cosmic events like black hole mergers, stretch and compress space as they travel across the universe. By measuring these subtle distortions, scientists can gather invaluable data on the properties of black holes, including their mass, spin, and behavior. The detection of gravitational waves has opened an entirely new window into understanding black holes, providing us with a deeper view of these mysterious entities. As technology advances, so does our understanding of black holes, with milestones such as the Event Horizon Telescope capturing the first ever image of a black hole's shadow in 2019. We are edging ever closer to unlocking the secrets of these cosmic behemoths. Each new discovery challenges our perceptions, pushing the boundaries of physics and revealing the profound mysteries of the universe. Black holes have long presented a paradox for physicists. At the core of these objects lies a singularity, a point where gravity becomes infinitely strong, and space-time itself curves beyond our ability to describe or understand using current physical theories. The laws of physics, as formulated by Einstein and others, were developed without fully accounting for the existence of such extreme entities. The singularity at the heart of a black hole is a point where our equations break down, and we are left without a comprehensive framework to explain what happens there. This raises significant questions about the future of our understanding of the natural world, indicating that we may need a more unified theory that bridges the gap between general relativity, which describes gravity, and quantum mechanics, the theory of the very small. Furthermore, black holes introduce a fascinating dilemma in the field of quantum mechanics. According to quantum theory, information cannot be truly lost. It must always be preserved in some form. However, when matter falls into a black hole, it appears to vanish entirely, seemingly contradicting this principle. This puzzle, known as the information paradox, challenges our foundational understanding of physics and pushes scientists to reconsider the very nature of reality itself. Researchers are currently exploring a variety of ideas to resolve this paradox, but as of now, it remains one of the greatest unresolved mysteries in theoretical physics. Black holes, thus, are not only objects of intense gravitational forces, but also the catalysts for new theories that could lead to a unified understanding of the cosmos. As scientists probe deeper into these enigmatic phenomena, they are not just studying the black holes themselves, but are also questioning the very nature of space, time, and existence. Each discovery brings us closer to a theory that could fundamentally change our conception of the universe, unlocking insights that have the potential to alter our understanding of reality. One of the most crucial concepts in the study of black holes is the event horizon. This is the boundary surrounding a black hole, beyond which no matter or radiation can escape. Once an object crosses the event horizon, it is effectively isolated from the rest of the universe, trapped in the black hole's gravitational grasp. The event horizon serves not just as a physical boundary, but also as a symbolic point of no return, further emphasizing the mysterious nature of black holes. An especially intriguing aspect of the event horizon is its relationship with light. Light, which travels at the fastest speed in the universe, cannot escape from within this boundary. This leads to the remarkable phenomenon of black holes appearing black, as they do not emit any light of their own. However, they do warp and distort light from surrounding stars, an effect that allows astronomers to infer the presence of a black hole and study its properties. For instance, as matter is pulled toward the black hole, it heats up and emits radiation that can be detected by powerful telescopes, providing us with important clues about the environment surrounding the black hole. The event horizon also has profound implications for our understanding of time and space. According to the theory of general relativity, as an object approaches the event horizon, the gravitational forces intensify dramatically. This leads to the phenomenon of time dilation, where time appears to slow down significantly for an observer falling into the black hole compared to someone watching from a safe distance. This curious interaction between time and gravity raises fundamental questions about the nature of the universe and challenges our conventional understanding of how the laws of physics operate at extreme scales. In conclusion, black holes are not just enigmatic objects of cosmic interest, but also fundamental to our quest for a deeper understanding of the universe. The event horizon, the singularity, and the paradoxes they present continue to inspire research that could one day lead to a new and unified theory of everything, a theory that could revolutionize our perception of space, time, and reality itself. As we continue to probe these cosmic giants, each new discovery brings us closer to unlocking the deepest secrets of the cosmos. The study of event horizons in black holes is not just a niche inquiry in theoretical physics. It contributes significantly to broader questions about the very nature of information itself and its preservation across the cosmos. One of the most puzzling and fascinating aspects of this area of research is the fate of information when it crosses the event horizon, the boundary beyond which nothing, not even light, can escape the gravitational pull of a black hole. This mystery has captivated physicists for decades, And as our exploration of black holes deepens, the event horizon remains a focal point, offering not just clues about these enigmatic cosmic giants, but also shedding light on the fundamental principles of the universe itself. Supermassive black holes, those colossal behemoths sitting at the centers of galaxies, are born through a series of complex and fascinating processes that unfold over unimaginable stretches of cosmic time. It all begins with the collapse of massive clouds of gas and dust in the early universe. These clouds, predominantly composed of hydrogen and helium, succumb to gravity, leading to the birth of the first stars. When these massive stars reach the end of their life cycle, they explode in brilliant supernovae, leaving behind dense remnants known as stellar black holes. As the universe ages and evolves, these stellar black holes, through a slow yet powerful process of merging, gradually combine to form more massive black holes. But the story doesn't end there. In the dense and tumultuous environments of early galaxies, these stellar black holes didn't simply sit idly by. They began to accrete matter, gathering surrounding gas, dust, and even entire stars. This process of accretion, which involves the continuous accumulation of mass, not only increases the size and mass of the black holes, but can also result in the production of enormous amounts of energy. This energy is emitted as radiation, which can light up the central regions of galaxies, creating what we know as quasars. These are some of the brightest and most powerful objects in the universe, visible even across vast distances. Over the course of millions of years, the supermassive black holes at the centers of galaxies evolve through intricate interactions with their environments. As galaxies collide and merge, their central black holes can also merge, forming even more massive, supermassive black holes. It is now understood that nearly every large galaxy, including our very own Milky Way, is home to one of these powerful entities. Yet the exact mechanisms by which these black holes grow remain a subject of intense study. Scientists are exploring various possibilities, such as the inflow of gas from the surrounding space, the merging of stars, and even interactions with mysterious forms of matter, like dark matter. Interestingly, these supermassive black holes might not be mere passive observers in the universe. Evidence suggests that their feedback, particularly the energy released as matter spirals into them, can have profound effects on the evolution of their host galaxies. This energy can influence the rate of star formation within the galaxy and even affect the overall growth of the galaxy itself. This intricate interplay between black holes and their surrounding environments underscores the fact that these cosmic giants are not just passive participants, but active players in the ongoing evolution of the universe. In a way, the formation and growth of supermassive black holes offer us not only answers to fundamental questions about black holes themselves, but also provide deep insights into the history and evolution of galaxies and the universe as a whole. One of the most exciting frontiers of astrophysics today involves the study of gravitational waves, ripples in the very fabric of space-time itself. These waves are generated by some of the most violent and energetic events in the universe, including the merger of black holes. When two black holes spiral toward each other and eventually collide, they release an enormous amount of energy. This energy propagates outward as gravitational waves, traveling across the universe, carrying with them crucial information about the event that produced them. The detection of gravitational waves has revolutionized our understanding of black holes and the events that shape them. These waves allow scientists to gather invaluable data about the properties of the black holes involved in a merger, including their masses and spins before they collide. This ability to measure such characteristics helps researchers piece together the origins and evolution of these black holes, providing insights into the environments from which they emerged. More than that, the precise wave patterns offer clues about the dynamics of the merger itself. By studying the frequencies and amplitudes of the gravitational waves, scientists can infer the complex interactions between the black holes during their final moments. This helps answer questions like whether the black holes came from the same stellar population or if their merger was influenced by other factors, such as nearby stars or gas. Each new detection of gravitational waves serves as a new chapter in our quest to understand these cosmic mysteries. With every discovery, we refine our knowledge of black hole physics and expand our comprehension of the universe's history. As more black hole mergers are observed, we are able to construct a more complete and nuanced picture of these enigmatic objects and their profound role in shaping the cosmic landscape. Black holes are not just cosmic oddities. They hold immense sway over the galaxies they inhabit. At the heart of most galaxies lies a supermassive black hole, with a mass equivalent to millions or even billions of stars. These titanic entities exert a gravitational pull so strong that they can attract surrounding matter, pulling gas, dust, and even stars into their immense gravitational well. But the influence of black holes extends far beyond this. As matter spirals into a black hole, it heats up and forms an accretion disk. This disk emits tremendous amounts of energy, which can trigger powerful jets of matter that shoot outward from the black hole's poles. These jets can extend far beyond the galaxy's core, impacting the interstellar medium and dispersing energy across vast distances. This energetic outflow plays a crucial role in the life cycle of galaxies. The shock waves produced by these jets can compress nearby gas clouds, potentially sparking new star formation in regions that were previously inactive. In this way, black holes act as both creators and destroyers, shaping the birth and death of stars and influencing the overall structure and evolution of their host galaxies. In the grand scheme of the universe, black holes are much more than just points of no return. They are fundamental forces that shape the very fabric of galaxies, influencing the creation of stars, the development of galaxies, and the overall progression of cosmic history. Through the study of black holes, we continue to peel back the layers of the universe's most profound mysteries, uncovering truths about the forces that govern everything from the smallest particles to the largest cosmic structures. The presence of a supermassive black hole at the heart of a galaxy plays a crucial role in maintaining the overall stability and structure of that galaxy. As stars orbit around the black hole, they form a dynamic system that provides the gravitational force necessary to hold the galaxy together. This gravitational interaction between the stars and the black hole is vital to the organization of the galaxy. Without this balance, the galaxy could collapse under its own weight. It's not just the stars orbiting around it, but also the continuous exchange of energy and mass between the black hole and its surrounding environment that sustains the galaxy's integrity. What's fascinating is that the growth of a black hole is closely tied to the evolution of the galaxy it inhabits. As galaxies evolve over billions of years, their black holes tend to grow at a pace that mirrors the development of the stellar populations within them. This suggests that the fate of stars and black holes is deeply intertwined in a kind of cosmic dance, where the presence and behavior of one directly influence the other. This relationship highlights the essential role black holes play in shaping the architecture of galaxies, making them far more than just strange, isolated phenomena. They are, in fact, fundamental to the larger narrative of the universe's formation and its ongoing evolution. The discovery of Hawking radiation, proposed by physicist Stephen Hawking in the mid-1970s, significantly altered our understanding of black holes. For centuries, black holes were perceived as cosmic vacuums, powerful enough to consume everything in their vicinity, including light. Nothing, not even light itself, could escape their immense gravitational pull. But Hawking's revolutionary theory introduced the idea that black holes could emit radiation thanks to the principles of quantum mechanics. This radiation arises from virtual particles that spontaneously form near the event horizon, the point beyond which nothing can escape the black hole. When one of these particles is sucked into the black hole, the other escapes, creating what we now know as Hawking radiation. The implications of this discovery are profound. First, it challenges the long-held belief that black holes are completely black and permanent. If they can emit radiation, it follows that black holes can slowly lose mass and energy over time. This leads to the groundbreaking suggestion that black holes might eventually evaporate entirely, shrinking down to nothing. This possibility of black hole evaporation challenges traditional views and contributes to the ongoing debate about the life cycle of these cosmic giants. Moreover, Hawking's discovery raises critical questions about the fate of information that falls into a black hole. According to classical physics, once something crosses the event horizon, it is lost forever. But quantum mechanics asserts that information cannot be destroyed. This contradiction gives rise to the famous black hole information paradox. If Hawking radiation allows for the escape of information, it could open the door to revolutionary insights about the very nature of reality itself, potentially reshaping our understanding of the universe's fundamental laws. Hawking radiation also redefines the relationship between black holes and thermodynamics. Black holes can now be viewed as thermodynamic objects, possessing entropy, a concept that links them to the laws governing energy and information. This connection has inspired new avenues of research for particularly efforts to reconcile the principles of general relativity with quantum mechanics. This challenge could bring us closer to a unified theory of physics, one that explains all fundamental forces within a single framework. The concept of black holes as cosmic gateways, or wormholes, introduces another captivating dimension to our understanding of these enigmatic objects. Black holes are often depicted as regions in space where the gravitational pull is so intense that nothing, not even light, can escape. This extraordinary force results from the collapse of massive stars that have exhausted their nuclear fuel. However, black holes also inspire theories about the possibility of wormholes, hypothetical passages through space-time that might serve as shortcuts between distant regions of the universe. According to certain interpretations of Einstein's theory of general relativity, a black hole could theoretically connect to another point in space-time, functioning as a wormhole. Such a connection might allow matter or information to travel vast cosmological distances in a fraction of the time it would normally take. However, the idea of black holes functioning as wormholes remains speculative and fraught with challenges. One significant hurdle is the question of stability. For a wormhole to be traversable, it would require a special form of matter known as exotic matter, which would have negative energy density. This exotic matter would prevent the wormhole from collapsing under the immense force of gravity, allowing safe passage. To date, exotic matter has yet to be observed, making the practicality of wormholes highly uncertain. Moreover, even if a traversable wormhole were to exist, it would likely be transient, unstable, and only open for a brief moment, making intergalactic travel seem incredibly difficult, if not impossible. Despite these obstacles, the idea of black holes as potential gateways continues to captivate the imagination. It encourages further exploration into the nature of the universe and the possibility that there are aspects of space-time that we have yet to fully comprehend. In recent years, the imaging of the supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A*, has sparked both mystery and fascination. With a mass approximately 4 million times that of the Sun, Sagittarius A is a colossal presence within our cosmic neighborhood. For decades, astronomers have theorized about the role of supermassive black holes in the evolution of galaxies. However, the details surrounding the behavior and structure of Sagittarius A remain elusive. One of the primary mysteries involves the interaction between the black hole and the stars orbiting around it. Observations have shown that these stars are moving at astonishing speeds, suggesting that an incredibly massive object is influencing their orbits. Yet, the specifics of how Sagittarius A exerts its gravitational pull remain unclear. What do these interactions reveal about the relationship between black holes and the stars that surround them? How do black holes shape the formation and dynamics of their galactic neighborhoods? Another intriguing aspect of Sagittarius A is its relatively calm appearance, especially when compared to other black holes that are known for their explosive energy outputs and jets of radiation. This quieter demeanor has led scientists to ask whether this black hole is consuming matter at such a slow rate that it remains undetectable, or if there is some other mechanism at work. Recent imaging has provided evidence of hot gas spiraling into the black hole, but the exact nature of this accretion process remains an enigma. As we continue to delve deeper into the mysteries of black holes and the intricacies of space-time, the enigmatic behavior of Sagittarius A may hold the key to unlocking a deeper understanding of the universe's most elusive objects. With each new discovery, we move a step closer to unraveling the secrets of these cosmic giants, and perhaps to revealing the hidden workings of the universe itself. The study of Sagittarius A star, the supermassive black hole at the center of our galaxy, along with its many mysteries, invites us to think on a much grander scale. By understanding the nature of black holes like Sagittarius A star, we unlock crucial insights into the very formation and evolution of galaxies, including our own Milky Way. As researchers continue their work, sifting through the vast amounts of data gathered from monumental imaging projects, we are left to anticipate the revelations that may emerge, pushing the boundaries of our comprehension about the cosmos. These discoveries promise to reshape the way we view the universe itself. The concept of an expanding universe emerged in the early 20th century, forever altering our perspective on the cosmos. One of the earliest pieces of evidence for this came from the American astronomer Edwin Hubble, who made a groundbreaking discovery. Galaxies are moving away from us in all directions. This was deduced by carefully analyzing the light emitted by distant galaxies, revealing a phenomenon known as redshift. When light waves stretch as an object moves away from an observer, they shift toward the red end of the spectrum. The farther away a galaxy is, the faster it seems to recede, providing a compelling indication that the universe itself is expanding. Another key piece of evidence supporting the theory of an expanding universe comes from the cosmic microwave background radiation, CMB. Discovered in the 1960s, this faint glow of radiation permeates the universe and is a remnant from a time shortly after the Big Bang. The CMB offers a snapshot of the universe when it was just like 300,000 years old, capturing the state of the cosmos in its infancy. The uniformity of this radiation, along with slight temperature fluctuations, serves as evidence for the Big Bang theory and strengthens the idea of an expanding universe. These minute variations in temperature provide clues about the early stages of cosmic structure, hinting at the seeds that would eventually grow into galaxies and clusters of galaxies. In addition to these observations, the discovery of supernova, particularly Type 1a supernova, has further enhanced our understanding of cosmic expansion. Supernova, the explosive deaths of massive stars, have been found to act as standard candles for measuring astronomical distances. By analyzing the brightness of distant supernovae, astronomers realized that these stellar explosions appear dimmer than expected, leading to the conclusion that the expansion of the universe is not merely continuing, it is accelerating. This unexpected acceleration has led scientists to explore the concept of dark energy, a mysterious force believed to be driving this rapid expansion. Taken together, these pieces of evidence, the redshift observed by Hubble, the cosmic microwave background radiation, and the behavior of distant supernova, form a compelling picture of a universe that is dynamic, not static. The idea that space itself is stretching continuously challenges our understanding of physics and raises profound questions about the fate of the cosmos. What forces are at play in shaping the universe's expansion? What will be its ultimate end? The discovery of dark energy has added another layer of complexity to our understanding of the universe. Before its discovery, scientists believed that gravity, the force pulling matter together, would eventually slow down the expansion of the universe. However, in the late 20th century, observations began to contradict this notion, unveiling a startling truth. Not only is the universe expanding, but its expansion is accelerating. This discovery left astronomers grappling with a force they had not anticipated, a force that we now call dark energy. Dark energy is believed to constitute about 70% of the total energy density of the universe, making it a dominant force in the cosmos. It creates a repulsive effect that counteracts the attractive force of gravity on a large scale, driving the universe's accelerated expansion. The implications of dark energy are vast and far-reaching. If dark energy remains constant over time, the universe will continue to expand indefinitely, with galaxies drifting farther and farther apart. This could eventually lead to a cold, dark, and empty universe, a scenario sometimes referred to as the heat death of the cosmos. The discovery of dark energy has sparked a surge of scientific inquiry into its true nature. Scientists are exploring whether dark energy is a constant force, a fluctuating field, or even a manifestation of some deeper, unknown physical principle. Various theories have emerged, from modifications to gravity itself to the possible existence of additional dimensions beyond the familiar three. Each hypothesis opens up new avenues for research, challenging our understanding of fundamental physics and driving innovation in cosmology. As scientists continue to probe the mysteries of dark energy, they refine our understanding not only of the universe's current state, but also of its ultimate fate. Ultimately, the discovery of dark energy has not merely added complexity to astrophysics. It has ignited a quest to unravel one of the most profound mysteries of existence. It has captured the imaginations of both scientists and enthusiasts alike, raising questions about the very fabric of reality and our place within it. The cosmic microwave background, CMB, often abbreviated as CMB, remains one of the most significant pieces of evidence in our understanding of the universe's history. This faint glow of radiation, which fills the entire universe, is a relic from a time when the cosmos was just a hot, dense soup of particles. Approximately 388,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine into hydrogen atoms. This allowed light to travel freely for the first time, marking the release of the CMB. By studying the tiny variations in temperature across the CMB, researchers can glean critical information about the distribution of matter in the early universe. These fluctuations, though minuscule, are essential clues in our understanding of how galaxies formed and evolved over billions of years. The CMB, in essence, acts as a cosmic fingerprint, revealing the universe's earliest moments and providing a blueprint for its ongoing evolution. As we continue to study the CMB and other phenomena like dark energy, Sagittarius A, ST, and supernovae, we move closer to understanding the vast, intricate forces that govern the universe, unveiling truths that have long remained hidden and pushing the boundaries of what we know about the cosmos. The cosmic microwave background, CMB, is far more than just a remnant of the early universe. It is a cornerstone of Big Bang cosmology, providing vital evidence that supports the theory. Its nearly uniform distribution across the sky suggests a level of homogeneity in the early universe, a concept that forms the foundation of many models of cosmic evolution. By studying the CMB, scientists can refine their understanding of key parameters of the universe, its age, composition, and the rate at which it is expanding. These insights allow cosmologists to unravel the complex and intricate history of our cosmos, offering a clearer view of how it has evolved over time. In essence, the CMB is a snapshot of the universe at a very young age, a relic of the primordial past that continues to inform our understanding of the cosmos. It's not merely an echo of the Big Bang, but a powerful tool that cosmologists use to unlock the deepest secrets of the universe. Through this ancient light, they uncover the fundamental principles that govern the universe's behavior, providing clarity in an otherwise mysterious and vast cosmic expanse. The CMB also continues to inspire new questions and discoveries, with each revelation revealing another layer of the universe's profound nature, much like peeling back the petals of a cosmic flower. Understanding the rate of expansion of the universe is a pivotal challenge in cosmology. A key tool in this endeavor is the redshift of light emitted from distant galaxies. When astronomers observe the light from these galaxies, they discover that it has shifted toward longer wavelengths. This shift, known as redshift, occurs due to the Doppler effect, an indicator that the galaxies are receding from us. The farther a galaxy is, the more its light is stretched, providing critical clues about its velocity and movement relative to Earth. By measuring the amount of redshift, scientists can calculate how fast a galaxy is moving away. Once the motion of these galaxies is established, cosmologists turn to Hubble's law, which posits a direct relationship between a galaxy's distance from us and its speed. In simple terms, the farther a galaxy is, the faster it appears to be moving away. This law, first discovered by American astronomer Edwin Hubble in the early 20th century, revolutionized our understanding of a constantly expanding universe. By plotting the redshift data against the distances to various galaxies, scientists can create the Hubble diagram, an essential tool that illustrates this extraordinary relationship. Another pivotal piece of evidence comes from the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient radiation provides crucial information about the universe's early state and ongoing expansion. By analyzing the CMB, scientists can estimate the rate of expansion, known as the Hubble constant. Furthermore, other techniques, such as observations of supernovae and gravitational lensing, help refine the accuracy of these measurements, adding depth to our understanding of the universe's dynamics. In a fascinating twist, recent research has uncovered a surprising truth. The rate of expansion is not constant. In fact, the universe is expanding at an accelerating pace, which implies the existence of a mysterious force known as dark energy. This discovery has had profound implications for cosmology, reshaping our understanding of the forces at play in the cosmos. The realization that the universe's expansion is accelerating opens up new avenues of exploration, inviting scientists to investigate the nature of dark energy and how it influences the universe's ultimate fate. As we continue to explore the cosmos, the expanding nature of the universe presents both profound questions and profound revelations. The fact that the universe is speeding up in its expansion carries significant implications for its future. As galaxies continue to recede from each other, their separation will only grow. In time, the expansion of the universe will lead to the isolation of galaxies, with those in our own local group eventually drifting apart into the vastness of space. Over immense periods, the visible universe will become increasingly desolate, consisting mainly of the remnants of dead stars and black holes, an eerie shadow of the vibrant cosmos we observe today. Dark energy, which makes up roughly 70% of the universe, remains one of the greatest mysteries in modern science. Its true nature is still elusive, despite its profound impact on cosmic expansion. As the universe expands at an ever-accelerating rate, the structures that we know today will inevitably change. Stars will exhaust their nuclear fuel and cease to shine, galaxies will drift further apart, and the universe will evolve into a very different state. The future of the universe is still unknown, but one thing is certain. As we continue to observe and measure the cosmos, we will continue to uncover new layers of understanding about its vast and ever-changing nature. In contemplating the ultimate fate of the universe, one scenario that stands out is the Big Freeze. In this chilling projection, as galaxies drift ever further away from us, receding beyond our observational horizon, the night sky will gradually lose its brilliance. The once vibrant tapestry of stars will fade, and the vast emptiness of space will take over. As time marches on, stars will burn out, one by one, and the grand cosmic spectacles that once filled the universe with awe will become an increasingly rare occurrence. Over countless eons, the universe will continue to cool, erasing all that we now cherish in the cosmic landscape. Only the most massive remnants, such as black holes, might persist, lingering like ancient monuments in a desolate void. Even these immense objects will eventually succumb to the relentless march of time, dying slowly through a process known as Hawking radiation. The once active universe will transition into an almost unimaginable state of cold, dark emptiness, an existence defined by silence and the slow, inevitable fading of all things. An alternative fate, equally unsettling, is the Big Rip. In this scenario, the accelerated expansion of the universe doesn't slow down, but instead intensifies, pushing outward with ever-increasing force. The very fabric of space-time itself would begin to tear apart. Galaxies, stars, and even atoms, those fundamental building blocks of matter, would be ripped asunder in a cataclysmic unraveling of the cosmos. In the final moments, the universe would reach a singularity, a point where all the familiar concepts of space and time break down entirely. Here, the laws of physics as we understand them would cease to hold, and everything we know would collapse into a state beyond comprehension. These two potential endings to the universe, the Big Freeze and the Big Rip, are built upon the principles of modern cosmology. Yet they also underscore the limitations of our current understanding of the universe. Despite our sophisticated models and observations, we still have so much to learn about the vastness of space and the future that awaits. In the quest to understand this future, scientists look to galaxy clusters, some of the largest and most complex structures in the cosmos. These colossal formations, consisting of hundreds to thousands of galaxies bound together by gravity, serve as cosmic laboratories. Their immense mass creates powerful gravitational fields, influencing not only the galaxies within them, but also the dark matter that pervades the universe. By studying the distribution, formation, and dynamics of galaxy clusters, astronomers can unlock the secrets of the universe's architecture. These clusters act as cosmic beacons, helping us map the large-scale structure of the universe and understand the forces at work within it. The locations and distribution of galaxy clusters serve as markers, revealing the hidden gravitational forces that shape the cosmos, forces driven by both visible matter and the elusive dark matter. The study of these massive clusters offers invaluable insights into the evolution of the universe, from the earliest moments following the Big Bang to the present day. These clusters also provide critical clues about the role of dark energy, a mysterious force believed to be driving the accelerated expansion of the universe. As researchers observe how clusters form and grow, they can refine models of cosmic evolution, exploring the intricate balance of forces that shape the universe and ultimately its future. Engaging with these massive structures not only enriches our understanding of the universe's past, but also provides essential insights into the forces that will determine its fate. Every cluster that is detected offers a new chapter in the ongoing story of the cosmos, illuminating the dynamics that drive its expansion and helping us piece together the puzzle of its origins and future. Equally fascinating are the vast, empty regions of space known as cosmic voids. These immense expanses, almost entirely devoid of galaxies, offer a rare opportunity to study the universe in a completely different way. These voids can stretch hundreds of millions of light years across, dwarfing the dense galaxy clusters that populate other parts of the universe. They are a stark contrast to the bustling, crowded galactic environments found elsewhere in the cosmos, making them an intriguing subject of study for cosmologists. By analyzing these voids, scientists can gain a deeper understanding of the universe's composition and its evolution over time. In particular, cosmic voids offer important clues about dark energy and dark matter, two of the most mysterious components of the universe. As voids grow larger, they reveal regions where gravity is weak, allowing researchers to observe how matter and energy have evolved since the Big Bang. These vast, empty regions act as a canvas for the universe, showing how the large-scale structure of the cosmos has been shaped by the interplay between gravity and the accelerated expansion driven by dark energy. Despite their emptiness, cosmic voids still contain small amounts of matter such as gas and dust, and studying these materials can reveal crucial information about the distribution of dark matter. Although invisible to our eyes, dark matter makes up roughly 27% of the universe, and its influence can be seen in the structure of voids. The gravitational effects of dark matter are felt even in these empty regions, offering insights into its role in the evolution of the universe. Exploring cosmic voids is akin to listening to the quietest parts of a symphony. In the absence of the usual cosmic sounds, we uncover hidden truths about the nature of the universe. These vast emptinesses help bridge the gap between visible matter and the mysterious forces, like dark matter and dark energy, that govern the cosmos. By studying voids, we not only learn about the structures that populate the universe, but also deepen our understanding of its fundamental components. The scale of the universe, in all its vastness, remains one of the most profound challenges to human understanding. The universe is so immense that it defies our ability to truly grasp its size. When we gaze up at the night sky, we are looking at stars that are not merely millions, but billions of light years away. The distance between us and these distant objects is incomprehensible to our everyday experience, where most of our interactions occur within just a few miles or kilometers. To put this in perspective, consider that there are an estimated 100 billion galaxies in the observable universe, each containing millions to trillions of stars. If we were to try to imagine the number of stars in the universe, it would far exceed the total number of grains of sand on all the beaches of Earth. This staggering fact forces us to reckon with our place in the cosmos. We are but one small planet orbiting an ordinary star, situated in an unremarkable galaxy, adrift in an incomprehensibly vast universe. This enormity invites a deeper reflection on human significance. What role do we play in the grand cosmic narrative? And how do we make sense of such a vast scale, where the distances and numbers involved exceed anything we can truly comprehend? The challenge is not just about understanding the universe's size, but also about communicating it in meaningful ways. One example is the light year, a unit of distance that measures how far light travels in 1 year. This concept can be difficult to grasp, especially when we consider that the nearest star to us, Proxima Centauri, is over 4 light years away. The light we see from it today left the star over 4 years ago, making the concept of time and distance in the universe profoundly different from anything we experience on Earth. As we continue to explore and measure the vastness of the universe, we are reminded that our understanding is still in its infancy. The more we discover, the more we realize how little we truly know about the cosmos and the forces that govern its existence. Yet, in this uncharted territory, we find both mystery and wonder, fueling the drive to explore the infinite unknown. Left behind more than 4 years ago, that distant star continues to shine, albeit in the past. For many, it's an almost unfathomable concept. The idea that when we gaze at stars, we are not observing them as they are now, but as they were when their light first began its journey across space, traveling toward us. This concept introduces an entirely new layer of complexity to our understanding of time and space, forcing us to confront the vastness of the universe on scales that stretch far beyond everyday experience. As we look further into the cosmos, it becomes apparent that our comprehension of the universe is limited without the aid of scientific tools and methods. Telescopes, satellites, and increasingly sophisticated simulations are the instruments we rely on to navigate the immense expanse of the universe. They enable us to piece together the intricate puzzle that is the cosmos, revealing insights that would otherwise remain hidden in the depths of space. Each discovery, whether big or small, plays a crucial role in expanding our knowledge and reshaping our understanding of the universe. This ongoing journey of exploration not only enriches our scientific grasp of the world around us, but also deepens our appreciation for the boundless mysteries that still await us. As we venture further, we are constantly reminded that the universe is vast and enigmatic, full of questions yet to be answered. One of the most perplexing enigmas in modern cosmology is the existence of dark matter. Invisible and undetectable by traditional means, dark matter does not emit or interact with electromagnetic radiation, making it impossible to observe directly with telescopes. Despite its elusiveness, it is believed to account for nearly 27% of the total mass and energy content of the universe. Although we cannot see it, dark matter's influence is undeniable. It plays a fundamental role in shaping the universe, helping to anchor galaxies and galaxy clusters, and influencing their formation and movement through gravitational interactions. To grasp the significance of dark matter, we must delve into the behavior of galaxies. When astronomers observe galaxies, they notice something strange. These massive structures are rotating at speeds far greater than what would be expected based solely on the visible matter they contain. If we were to account only for the stars, gas, and dust in these galaxies, their centrifugal forces would tear them apart. Something must be providing an additional gravitational pull to keep these galaxies intact, and that something is dark matter. Without it, the universe would be a very different place, with galaxies either failing to form altogether or being ripped apart by their own rotation. Further evidence of dark matter's existence is revealed through the cosmic microwave background radiation, a faint afterglow of the Big Bang. The patterns in this radiation give us crucial information about how matter, both visible and invisible, was distributed in the early universe. These patterns help scientists understand the formation of galaxies and the structure of the universe as it expanded from its initial fiery beginnings. Additionally, gravitational lensing, the phenomenon in which light from distant objects is bent by the gravity of a massive object in its path, provides further clues to dark matter's presence. As light bends around galaxies and clusters, astronomers observe that there is more mass present than can be explained by the visible stars and galaxies alone. Although dark matter's presence is widely accepted, its exact composition remains one of the most profound mysteries of modern physics. Numerous candidates have been proposed to explain its nature, with the most prominent being weakly interacting massive particles, WADI-EMPs. These hypothetical particles could account for the unseen mass that dark matter represents, but despite extensive efforts, no direct detection of dark matter has been made so far. This lack of a definitive discovery only deepens the allure of this cosmic mystery, fueling further investigation into the fundamental makeup of the universe. Exploring dark matter pushes the boundaries of our scientific understanding and challenges our perceptions of reality itself. By studying its effects on visible matter, radiation, and the large-scale structure of the universe, scientists are piecing together an ever-evolving picture of the cosmos. The most compelling evidence for dark matter comes from studying the behavior of galaxies. When astronomers observe the rotation of galaxies, they see that stars at the outer edges of these galaxies are moving much faster than would be expected based on the visible mass alone. This discrepancy suggests the presence of an unseen force, dark matter, exerting a gravitational influence on these distant stars. One of the most striking pieces of evidence comes from the study of galaxy clusters. When scientists calculate the mass of a cluster based on the visible galaxies and hot gas it contains, they find that the observed gravitational effects are far greater than what can be explained by the visible matter alone. This anomaly points directly to the existence of additional unseen mass, further supporting the presence of dark matter. Another key method used to study dark matter is gravitational lensing. When light from objects behind a massive galaxy cluster bends due to the cluster's gravity, astronomers can measure the degree of this bending to estimate the total mass of the cluster, including the dark matter. This technique has revealed that dark matter makes up roughly 26% of the universe, a striking contrast to the mere 5% composed of ordinary matter, the matter we are most familiar with, everything from stars and planets to the air we breathe. As we continue to explore these cosmic phenomena, dark matter remains a central puzzle in our quest to understand the universe. Despite our growing knowledge, the full nature of dark matter remains a tantalizing mystery, one that may one day hold the key to understanding not just the universe's structure, but the very fabric of reality itself. Until then, the search continues, and with each new discovery, we inch closer to uncovering the secrets of this invisible force that shapes the cosmos. Simulations exploring the formation and evolution of the universe have provided profound insights into the integral role of dark matter in shaping cosmic structures. These simulations, which model the universe's behavior on grand scales, align remarkably with observations of how galaxies are distributed across vast distances. Despite the fact that dark matter remains elusive and undetectable by traditional means, its gravitational influence on the matter we can see, stars, galaxies, and gas clouds, reveals an intricate web of evidence that continues to captivate and challenge scientists. Dark matter is among the most intriguing enigmas of modern cosmology. Comprising about 27% of the total mass and energy of the universe, it far outweighs the ordinary matter that makes up the stars, planets, and even the atoms of which we are composed. Yet for all its prevalence in the cosmos, dark matter resists direct detection. Its invisible nature, coupled with the lack of any interaction with electromagnetic radiation, renders it undetectable by telescopes or other traditional scientific instruments. Nonetheless, researchers have made substantial progress in their quest to understand this invisible force. One of the most ambitious experiments designed to uncover the secrets of dark matter is the Large Underground Xenon LUX experiment, located deep beneath the Earth's surface in South Dakota. The LUX-Zeppelin-LZ collaboration aims to detect dark matter particles by capturing their faint interactions with normal matter, using a tank filled with liquid xenon and advanced detection technologies. This setup relies on the notion that if dark matter particles collide with atoms of xenon, they will transfer enough energy to be detected by highly sensitive sensors. Similarly, in Italy, the cryogenic rare event search with superconducting thermometers, CREST-T, experiment is another innovative initiative. Situated deep underground, CREST is designed to detect the minute heat produced when a dark matter particle strikes the nucleus of a calcium tungstate crystal. These extraordinarily delicate measurements may provide the first direct evidence of dark matter's elusive nature. Beyond these efforts, other experiments like the Panda X in China and the Xenon experiment, which also uses liquid xenon, are running parallel searches. These labs are specifically built in underground locations to shield them from cosmic rays and other sources of interference that might obscure signals of dark matter. By using varied technologies and methods, these experiments contribute to a more nuanced understanding of what dark matter could be. As researchers continue to collaborate and innovate, the search for direct evidence of dark matter remains one of the most exciting frontiers in modern physics. Each new experiment, no matter how small, brings humanity closer to unlocking one of the greatest mysteries of the universe, illuminating how much there is yet to understand about the cosmos and the invisible forces that govern it. At the heart of this mystery is the stark contrast between dark matter and the ordinary matter that constitutes everything we see in the universe. Ordinary matter, composed of atoms, protons, neutrons, and electrons, interacts with the fundamental forces of nature, forming the building blocks of everything from stars to life itself. The gravitational pull of this ordinary matter leads to the creation of galaxies, solar systems, and other visible structures in the universe. In contrast, dark matter is completely invisible. It does not emit, absorb, or reflect light, which means it cannot be detected through conventional means. However, its existence is inferred primarily from its gravitational effects on visible matter. For example, astronomers have observed that galaxies spin at speeds that should, according to the laws of physics, tear them apart if only ordinary matter were responsible for their motion. Dark matter's gravitational pull provides the missing mass, explaining why galaxies remain intact rather than disintegrating under their own rotation. Dark matter plays a pivotal role in the formation of galaxies and large-scale cosmic structures. It is estimated that about 25% of the universe's total mass consists of dark matter, while ordinary matter contributes a mere 5%. This means that the majority of the universe's mass is invisible to us, yet it exerts a profound influence on the formation and behavior of galaxies, galaxy clusters, and cosmic filaments. One of the most crucial functions of dark matter is its role in the initial formation of galaxies. In the early universe, shortly after the Big Bang, slight fluctuations in density caused small pockets of matter to form. These regions, which were slightly denser than their surroundings, became gravitational attractors, drawing in more gas, dust, and matter. Dark matter's gravity provided the foundation for this process, concentrating in certain regions of space and encouraging the formation of the first galaxies. As matter clumped together, stars began to form, and the complex structures of the universe began to take shape. The gravitational influence of dark matter is so significant that it acts as a kind of cosmic scaffolding, holding galaxies together and preventing them from flying apart. Without this invisible mass, galaxies would simply disintegrate, unable to maintain their cohesive structure. Dark matter also plays an ongoing role in the dynamics of galaxies, affecting the way in which stars orbit around the galactic center. When astronomers study the rotation of galaxies, they notice that stars in the outer regions move faster than would be expected, based solely on the amount of visible matter present. This discrepancy is a clear indicator of dark matter's presence, as it provides the additional gravitational pull needed to explain these faster than expected rotations. The influence of dark matter extends far beyond individual galaxies. It is believed to play a significant role in the overall structure of the universe. Researchers now understand that dark matter forms a vast web-like framework that dictates how galaxies cluster and interact across cosmic distances. This cosmic web is composed of enormous filaments of dark matter that act as a structural backbone for galaxies, galaxy clusters, and superclusters. Understanding dark matter is therefore essential for unraveling the history of the universe and predicting its future. Without this mysterious substance, our comprehension of how galaxies formed and evolved would be incomplete. In essence, dark matter is the key to understanding the large-scale structure of the universe and how it will continue to evolve. As scientists refine their methods and tools, the quest to understand dark matter pushes the boundaries of knowledge. The development of new detection technologies and experimental approaches offers hope that in the coming years, researchers will finally be able to uncover the true nature of this elusive substance. Each step forward brings us closer to understanding the most fundamental components of the universe, those that, while invisible, play a defining role in the cosmic dance that has shaped everything we know. Without dark matter, the current configuration and diversity of galaxies would likely be fundamentally altered. In fact, studies on galaxy clusters have provided valuable insights into how dark matter influences the dynamics of these massive structures. Dark matter's significant gravitational pull is the key factor that holds galaxy clusters together, counteracting the outward pressure exerted by the hot gas that fills them. This gravitational balance is essential for maintaining the structure of these clusters and dictates how galaxies within them are organized, interact with each other, and move across the vastness of cosmic time. These gravitational forces are what shape the destiny of galaxies, influencing everything from their trajectories to their eventual mergers. Understanding dark matter is not merely a matter of unraveling the mechanics of galaxy formation and evolution, it also opens a window into the very nature of the universe itself. Despite being invisible and undetectable by current telescopes, dark matter constitutes roughly 25% of the universe's total mass energy content, making it one of the most intriguing and elusive components of the cosmos. Its presence is only detectable through the subtle gravitational effects it exerts on visible matter, such as galaxies and galaxy clusters. Researchers have developed several competing theories to explain what dark matter might be, but none has yet achieved universal acceptance. One of the most prominent theories proposes that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would interact only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. The hope is that these particles could be captured by specialized underground detectors, where their faint signals might be detected as they collide with ordinary matter. Despite the extensive and rigorous search efforts, including large-scale experiments conducted in underground laboratories worldwide, WIMPs have yet to be observed directly. Another promising possibility involves axions, lightweight particles that some theories in particle physics predict could account for dark matter. Axions are primarily theorized within the context of quantum chromodynamics, the study of the fundamental interactions between quarks and gluons. These particles might form what is known as axion clouds, which could manifest as specific types of waves. If axions do exist, they could provide a solution not only to the mystery of dark matter, but also to some of the fundamental questions in physics, such as explaining the peculiar behavior of the strong force. Additionally, a more radical theory suggests that primordial black holes formed in the intense conditions of the early universe could contribute to the dark matter density. These black holes, which range in size from a few times the mass of our sun to potentially millions of solar masses, would be scattered throughout the universe. If they exist, they could provide another crucial piece to the puzzle of dark matter, offering insights into both the structure of the early universe and its current composition. As researchers continue to refine their observational instruments and experimental techniques, the quest to uncover the true nature of dark matter remains one of the most compelling frontiers in modern cosmology. Each discovery, each new piece of evidence brings us closer to understanding the hidden scaffolding of the universe itself. Parallel to these advances in cosmology, the search for extraterrestrial life has made remarkable progress, thanks in large part to the evolution of technology. Perhaps one of the most groundbreaking developments in recent years is the enhancement of space telescopes. Instruments such as the James Webb Space Telescope have opened up new realms in astronomy, enabling us to peer into the atmospheres of distant exoplanets. This advanced technology allows scientists to analyze the chemical composition of gases in these far-off worlds, searching for biosignatures, chemical indicators that suggest the presence of life as we know it. In addition to space telescopes, the rapid progress in artificial intelligence and machine learning has transformed the way scientists analyze vast amounts of astronomical data. With thousands of exoplanets cataloged, AI systems can process and sift through past observations to predict which of these worlds are most likely to harbor life. By identifying patterns and correlations that might go unnoticed by human researchers, AI is accelerating our search for habitable planets, offering new insights into the cosmos and the potential for life beyond Earth. The role of robotic exploration in the search for extraterrestrial life cannot be overstated. Rovers and landers, such as NASA's Perseverance on Mars, are equipped with advanced instruments designed to analyze the chemical makeup of the soil and atmosphere of distant planets. These robots collect samples, conduct experiments, and test for organic compounds, providing us with vital information about the habitability of other worlds. Such technology opens a window into understanding whether life might exist, or may have existed, elsewhere in the solar system. Another significant leap forward has come in the form of communication technologies, which have reshaped how we search for signs of extraterrestrial intelligence. Projects like the Search for Extraterrestrial Intelligence, SETI, use powerful radio telescopes to listen for signals from intelligent civilizations. Innovations in signal processing now allow scientists to filter out background noise, enabling them to identify potential communications from distant stars. With these advancements, the dream of making contact with extraterrestrial life seems closer than ever. As technology continues to evolve, our prospects for discovering extraterrestrial life grow ever more promising. Astrobiologists are continually pushing the boundaries of our understanding, refining the criteria for what makes a planet habitable. A central focus of this research is the identification of exoplanets, planets that orbit stars outside our solar system. Detecting these distant worlds is no easy feat, but several methods have been developed to improve our chances. The transit method, for example, involves measuring the dimming of a star's light when a planet passes in front of it. This method provides crucial information about the planet's size, orbit, and composition. Another approach, known as radial velocity, detects the subtle wobble of a star caused by the gravitational pull of an orbiting planet. Both methods have proven invaluable in identifying exoplanets, but they are only the beginning of the search. Once exoplanets are discovered, astrobiologists focus on key factors that contribute to a planet's habitability. The most important of these is the planet's location within what is known as the habitable zone, or the Goldilocks zone, the region around a star where conditions are just right for liquid water to exist on a planet's surface. Since water is considered essential for life as we know it, this zone has become the primary target in the hunt for potentially habitable exoplanets. Planets within this zone may have the conditions necessary to support life, making them prime candidates for further study in the ongoing search for life beyond Earth. The convergence of technological advancements in space exploration, data analysis, and communication gives humanity unprecedented tools to explore the universe and perhaps discover life beyond our own planet. The future of astrobiology is one of excitement, exploration, and groundbreaking discoveries that could forever change our understanding of life and our place in the cosmos. Scientists continue to explore the fascinating and complex characteristics of planets far beyond our solar system, searching for signs that might suggest the potential for life. The examination of these distant worlds includes a focus on key features like size, composition, and atmospheric conditions. Notably, rocky planets, those with a solid surface like Earth, are often considered more promising candidates for hosting life compared to gas giants, which are largely composed of gases and lack solid surfaces. In their quest to learn more about these far-off planets, researchers rely heavily on advanced technologies, such as the Hubble Space Telescope and the recently launched James Webb Space Telescope. These powerful instruments allow scientists to scrutinize the atmospheres of exoplanets by analyzing light spectra. By studying the way light interacts with a planet's atmosphere, they can detect the presence of specific gases, including oxygen, methane, and carbon dioxide. The presence of these gases is a strong indication of potential biological processes, as they are often produced or regulated by living organisms. Technological advancements are continuously improving our ability to detect and study exoplanets. As we learn more about the stars these planets orbit, focusing on aspects such as their age, stability, and radiation emissions, our understanding of the environments on these exoplanets deepens. This holistic approach not only sharpens our search for distant worlds that might harbor life, but also brings us closer to answering the profound question of whether humanity is truly alone in the universe. Adding another layer of insight into the potential for life beyond Earth are extremophiles, remarkable organisms that thrive in Earth's most extreme and hostile environments. These creatures defy conventional understanding, surviving in conditions that would be lethal to most other forms of life. From the boiling waters of hydrothermal vents deep in the ocean to the frigid, desolate expanses of Antarctica's ice and the highly acidic lakes of Chile, extremophiles prove that life can adapt to the most extreme environments imaginable. Studying these organisms provides scientists with invaluable lessons on the biochemical versatility of life. Many extremophiles possess unique adaptations that enable them to survive under extreme conditions. For instance, some microorganisms produce heat shock proteins that help them endure high temperatures, while others have membranes that maintain stability in extremely acidic or saline environments. These adaptations not only suggest that life could exist in a variety of environments across the cosmos, but they also expand our understanding of what types of conditions might support life beyond Earth. Furthermore, extremophiles have shown that life can survive in isolation for millions of years. Organisms found in permafrost or deep under the ocean demonstrate the persistence of life, even in environments where it seems impossible. This resilience offers hope for the existence of life on other planets or moons, such as Europa, one of Jupiter's moons, or Enceladus, a moon of Saturn, where liquid water and potential energy sources exist beneath layers of ice. The discovery that life can endure in such isolated conditions encourages scientists to expand the search for extraterrestrial life to include environments that were previously considered inhospitable. The study of extremophiles has not only reshaped our understanding of life on Earth, but also transformed our outlook on the universe. These organisms serve as a mirror, reflecting the resilience and adaptability of life in the face of seemingly impossible conditions. Their existence challenges us to reconsider the boundaries of habitability and reminds us that no matter how harsh the environment, the potential for life still exists. As we continue to explore our solar system and beyond, extremophiles continue to inspire scientific inquiries that may one day lead to the discovery of life beyond our blue planet. Their incredible survival mechanisms push the boundaries of what we thought possible, providing new perspectives on life's potential throughout the cosmos. Equally transformative is the growing field of exoplanet research, where the study of exoplanet atmospheres has revolutionized our approach to the search for extraterrestrial life. With the discovery of more exoplanets, worlds that orbit stars outside our solar system, scientists are increasingly focusing on analyzing the compositions of these distant planets' atmospheres. This process involves studying the light from a star as it passes through a planet's atmosphere during a transit, providing crucial information about the gases present. By identifying elements like oxygen, carbon dioxide, and methane, scientists can begin to evaluate whether a planet has the conditions necessary to support life as we know it. One key concept in this search is the idea of biosignatures, chemical indicators that suggest life may exist on a planet. For instance, the simultaneous presence of methane and oxygen could suggest biological activity, as these gases tend to react chemically and would not coexist for long unless continually replenished. Detecting such a combination in an exoplanet's atmosphere could be a strong indication that life is influencing the planet's environment. To aid in this search, researchers are developing increasingly sophisticated telescopes and instruments, including the James Webb Space Telescope. These advancements are helping scientists detect and analyze these vital biosignatures in exoplanet atmospheres, opening up new avenues for discovering life across the universe. However, the study of exoplanet atmospheres isn't limited to finding planets that are Earth-like. Researchers are also exploring the atmospheres of gas giants and icy worlds, which may harbor forms of life vastly different from those we are familiar with. This shift in thinking is expanding the range of environments under consideration, allowing scientists to entertain the possibility of biosignatures in places that were once thought to be unsuitable for life. By broadening the scope of what constitutes a habitable environment, scientists are developing a more inclusive understanding of where life might exist across the cosmos. In this context, the exploration of exoplanet atmospheres is driving us closer to a deeper understanding of life's potential in the universe. Each new discovery adds layers to the mystery of our cosmic neighborhood, pushing us to refine our methods and tools to study these distant worlds. As technology improves, the possibility of uncovering signs of life elsewhere becomes increasingly tangible, reshaping our understanding of life in the universe and our place within it. Looking at our own solar system, several celestial bodies remain intriguing candidates for the search for extraterrestrial life. Among the most promising are Europa, one of Jupiter's moons, and Mars, our closest planetary neighbor. These worlds offer tantalizing possibilities for life beyond Earth, providing us with exciting opportunities to continue our exploration and expand our understanding of life's potential across the cosmos. Enceladus, a small yet captivating moon of Saturn, has increasingly attracted scientific interest for its potential to harbor life. Each of these celestial bodies, Europa, Mars, and Enceladus, presents conditions that spark the imagination and raise compelling questions about the existence of life beyond Earth. Europa, one of Jupiter's icy moons, holds a secret beneath its frozen surface, a vast ocean of liquid water buried deep below the ice. This subsurface ocean is thought to be in contact with Europa's rocky mantle, creating an environment where the chemical reactions necessary for life could occur. The moon's surface is etched with cracks and scars, evidence of geological activity. This suggests that there may be hydrothermal vents beneath the icy crust, much like those found on Earth, which could support thriving ecosystems in the absence of sunlight. Mars, the red planet, has been a focal point in the search for extraterrestrial life for decades. Evidence from robotic missions suggests that liquid water once flowed across its surface, carving out ancient riverbeds and valleys. In recent years, the search has focused on investigating ancient lakebeds and polar ice caps in hopes of uncovering signs of past life. The discovery of seasonal methane emissions on Mars has added another layer of intrigue, as methane is often associated with biological activity on Earth. Could this methane be a byproduct of microbial life that once thrived there? Then there is Enceladus, where geysers erupt from the moon's southern pole, spewing water vapor and organic compounds into the cold void of space. These plumes are a tantalizing sign that beneath Enceladus's icy crust, a subsurface ocean may exist. Analyzing the composition of these eruptions could provide vital clues about the chemical building blocks necessary for life, potentially opening a window into the nature of life in the outer solar system. As our exploration techniques advance, our understanding of these fascinating worlds is rapidly expanding. The quest for microbial life on Mars and other moons has become a driving force in space exploration. This pursuit not only seeks answers about whether we are alone in the universe, but also challenges our very conceptions of life and its origins. To aid in this investigation, scientists are utilizing cutting-edge technology, innovative engineering, and cross-disciplinary collaboration to detect signs of life or its building blocks on other planets and moons. Mars remains a prime candidate for this search. Evidence suggests that liquid water once flowed freely across its surface, creating an environment that may have been capable of supporting microorganisms. Robotic missions, such as NASA's Perseverance rover, have been specifically designed to search for signs of life. Equipped with sophisticated tools, these rovers are capable of analyzing Martian soil and rock samples, examining their chemistry in real time. Among their most critical functions is the detection of organic molecules, key ingredients for life as we understand it. Beyond Mars, the search for life extends to the icy moons of the outer solar system, including Europa and Enceladus. These moons are believed to harbor subsurface oceans beneath their frozen exteriors. To study these distant worlds, upcoming missions like the Europa Clipper are poised to play a pivotal role. Equipped with state-of-the-art instruments, the Europa Clipper will analyze Europa's surface and ocean composition, searching for the necessary ingredients for life: water, carbon, and energy sources. These missions aim to deepen our understanding of whether life could exist on these moons, far removed from the warmth of the sun. The exploration of exoplanets, or planets outside our solar system, further broadens the scope of the search for life. Many of these exoplanets exist within the habitable zone of their parent stars, where conditions may be just right for life to take root. Powerful telescopes like the James Webb Space Telescope have opened a new chapter in this search, offering unprecedented views into distant worlds. By analyzing the atmospheres of these exoplanets, scientists are able to detect signs of water, methane, and other chemicals associated with life, building a detailed picture of their potential for habitability. This comprehensive strategy, which encompasses nearby planets, moons, and distant exoplanets, keeps the dream of discovering microbial life very much alive in the scientific community. Whether on Mars, Europa, Enceladus, or a far-off exoplanet, the hunt for life beyond Earth is one of the most thrilling endeavors of our time. The discovery of extraterrestrial life, whether simple microbes or complex organisms, would have profound implications for humanity. It would fundamentally challenge our understanding of life itself. For centuries, humans have pondered the origins of life on Earth and questioned whether we are truly alone in the cosmos. The discovery of even the simplest form of extraterrestrial life would expand our definition of what it means to be alive and redefine our place within the universe. Such a discovery would also have far-reaching philosophical and ethical consequences. Questions about the nature of consciousness, the morality of interacting with intelligent alien species, and the very essence of what it means to be human would take on new significance. Our religious and cultural narratives might be reshaped, forcing societies to reconsider ideas that have shaped them for millennia. The realization that life exists elsewhere in the universe could inspire a sense of unity, as humanity reflects on its shared existence within an infinitely vast and diverse cosmos. From a scientific perspective, the discovery of extraterrestrial life would spark a new renaissance in research and exploration. The fields of astrobiology, planetary science, and astronomy would experience a surge in activity, with scientists striving not only to understand the forms of extraterrestrial life, but also to learn how these organisms survive in environments vastly different from our own. This knowledge could yield insights into our own biological processes and ecosystems, potentially leading to groundbreaking advancements in medicine, agriculture, and environmental conservation. In the end, the search for life beyond Earth is not merely about finding other beings in the universe. It is a journey that forces us to reflect on our own existence, on the conditions that sustain life, and on the remarkable possibility that life may thrive in places far beyond our imagination. As we continue to explore the mysteries of the cosmos, we edge closer to answering the most profound question of all: are we truly alone in the universe? The discovery of extraterrestrial life, if it were ever to occur, would ignite a profound transformation in the way humanity views its place in the cosmos. This monumental discovery would likely spark intense discussions about our technological and communicative capabilities, especially if we were able to establish contact with an intelligent civilization. The mere potential for such an exchange of knowledge could catapult scientific advancements far beyond our current imagination. It would challenge us to rethink the very nature of our society, as humanity would find itself navigating uncharted territory: interstellar diplomacy. In the face of such a discovery, we would be forced to grapple with fundamental questions about cooperation, conflict, and mutual benefit on a cosmic scale that we have never encountered before. The very conversation surrounding extraterrestrial life would open a new chapter in human history, compelling us to not only reflect on who we are, but to reconsider who we aspire to be in a universe full of mysteries that have yet to be uncovered. Our understanding of life, consciousness, and the universe itself could be fundamentally altered as we prepare for interactions that are beyond our wildest imaginations. For decades, the search for extraterrestrial life has captivated both scientists and dreamers alike. At the heart of this pursuit lies the question of how we might communicate across the immense distances that separate us from other civilizations. One of the most widely explored methods is the use of radio signals, which can travel across vast stretches of space without requiring physical travel. This search, known as the Search for Extraterrestrial Intelligence, SETI, involves scanning the skies for any radio signals that might suggest the presence of alien life. Among the most intriguing ideas in the field is the possibility of broadcasting electromagnetic waves, focused signals directed at star systems that could potentially host habitable planets. By sending these messages into space, we might someday make our presence known to intelligent beings. However, this approach is not without its challenges. The signals we send would need to be understandable by civilizations that may be vastly different from our own. In order to ensure the messages could be deciphered, scientists have suggested encoding information using universal mathematical principles or incorporating recognizable patterns, such as prime numbers, which are likely to be universally understood. Another intriguing concept is the creation of physical beacons or spacecraft designed to carry messages to distant star systems. These beacons would remain in orbit or travel along a trajectory that would allow them to eventually reach extraterrestrial civilizations. Such a message would contain vital information about humanity, our culture, our history, and our understanding of the universe. This approach underscores the idea that communication with extraterrestrial intelligence might not be an instantaneous event, but rather a slow, deliberate process that requires immense patience and thoughtful planning. Beyond technology, the challenge of establishing meaningful communication with alien civilizations would also depend on finding a common language. Just as humans have developed diverse languages and symbols based on culture and experience, extraterrestrial life may have entirely different forms of communication. The field of xenolinguistics, studying potential languages of alien civilizations, opens up an entire realm of possibilities for how we might decode messages from the stars. Whether through complex symbols, sound waves, or even nonverbal methods, the potential for finding a common ground in communication is vast and tantalizing. As we explore these various methods, hope persists that one day we will bridge the immense gap between ourselves and other intelligent beings, fostering understanding across the unimaginable expanse of the universe. The quest to communicate with extraterrestrial life represents one of the most profound endeavors of humanity, a journey toward the unknown, driven by a shared desire to connect with other life forms, no matter how distant or different they may be. Meanwhile, the very fabric of the universe has its own captivating story, woven from the smallest particles to the grandest galactic structures. The birth of galaxies, for example, is a complex and awe-inspiring process that begins with some of the most basic building blocks of matter. Shortly after the Big Bang, the universe was filled primarily with hydrogen and helium atoms, along with a few trace elements. These primordial particles floated freely in the vast emptiness of space, where gravity began to take hold and set the stage for the formation of the first galaxies. Over millions of years, tiny irregularities in the density of these particles caused certain regions to attract more matter, initiating the process that would eventually give rise to galaxies. As gas and dust accumulated, regions began to form clumps, known as protogalaxies. While not yet fully formed, these protogalaxies represented the early stages of what would eventually become massive galactic structures. As they gathered more mass, their gravitational pull grew stronger, accelerating their growth, a process that mirrored a cosmic snowball effect. The more mass a protogalaxy acquired, the stronger its gravity, which in turn accelerated the accumulation of additional matter. Eventually, these protogalaxies began to collide and merge with one another, forming larger and more cohesive structures. During these violent encounters, tremendous amounts of energy were released, sparking the formation of new stars and triggering intense bursts of star formation. This phase of galactic evolution was marked by a flurry of activity, with young stars lighting up the darkness of the universe and enriching their surroundings with heavier elements forged in the heart of these stellar furnaces. Over billions of years, these processes coalesced to create the diverse array of galaxies that we see today. Galaxies now come in a wide variety of shapes and sizes, from the elegant spirals like our Milky Way to the massive elliptical galaxies that populate the far reaches of space. Understanding how galaxies form not only illuminates their own histories, but also provides insight into the broader history of the universe itself. Each galaxy holds a unique narrative, shaped by the intricate interplay of gravity, cosmic forces, and the fundamental particles that began as whispers in the fabric of space-time. The evolution of galaxies is a dynamic and captivating journey that spans billions of years, driven by a multitude of intertwined processes. At the heart of this cosmic transformation lies gravity, which is responsible for the collapse of vast clouds of gas and dust into dense structures that eventually give birth to stars. As these stars burn out and reach the end of their lives, some of them explode in supernova, scattering elements and materials back into space. This process enriches the interstellar medium, providing the raw material for the next generation of stars. Another crucial aspect of galactic evolution is the merger of galaxies. Throughout cosmic history, galaxies have not remained solitary entities. They collide and merge with one another, triggering bursts of star formation as gas clouds are compressed and heated. These mergers can drastically alter the shape and dynamics of the resulting galaxy, as the gravitational interactions between the two systems can reorganize star orbits and strip gas and stars from one galaxy, transferring them to another. In addition to these visible processes, dark matter plays an essential role in the formation and stability of galaxies. Dark matter, which constitutes about 27% of the universe's total mass and energy, exerts a gravitational influence that helps galaxies form and hold together. Although it cannot be seen directly, its presence is felt through its effect on the motion of stars and the structure of galaxies. The gravitational pull of dark matter halos provides the necessary framework for galaxies to grow, and its mass influences the rotation of galaxies, determining whether they will evolve into sprawling spirals, elliptical formations, or some other shape entirely. Over time, the dynamics of dark matter, in concert with visible matter, determine a galaxy's final shape and behavior. The environment surrounding a galaxy also plays a key role in its evolution. In regions where galaxies are densely packed together, known as galaxy clusters, interactions between galaxies occur more frequently, often leading to processes like galaxy harassment. In these crowded regions, galaxies lose gas, which impairs their ability to form new stars. In contrast, galaxies that are more isolated may develop unique characteristics influenced by internal processes. The life story of a galaxy is, therefore, a dynamic interplay between the gravitational forces of stars, the influence of dark matter, and the broader cosmic environment. Galactic collisions are among the most spectacular events in the universe, leaving lasting imprints on the structure and evolution of galaxies. When two galaxies collide, their gravitational pulls can create dramatic interactions, reshaping the very forms of stars, gas, and dust within them. These collisions often lead to the birth of new stars and the creation of elliptical galaxies, as the merging systems coalesce into a larger, unified entity. The Milky Way, for instance, is on a collision course with the Andromeda Galaxy. When this merger occurs, roughly 4 billion years from now, it will dramatically alter the structure and population of stars within our galaxy. This cosmic event will not only change the physical shape of the Milky Way, but could also have a profound impact on the orbits of individual stars, ultimately transforming our stellar neighborhood. Galactic collisions also affect the distribution of dark matter in the universe. As galaxies merge, the gravitational effects alter the concentration and distribution of dark matter, which in turn influences how galaxies cluster together. This interaction is a key factor in shaping the large-scale structure of the universe, where galaxies are arranged in vast groups and filaments, separated by immense voids. The universe is an ever-changing dynamic tapestry, woven together by these cosmic interactions. As we peer into the depths of space, we begin to appreciate how these magnificent events have sculpted not only individual galaxies, but also the very structure of the universe itself. Understanding the role of dark matter in these processes, though hidden from our direct perception, gives us crucial insight into the forces that shape the cosmos, revealing the interconnectedness of all things in this vast, mysterious expanse. Without the gravitational pull of dark matter, the universe's cosmic structure would be radically different. The formation of galaxies, for example, may never have occurred as we know it. Dark matter's invisible presence exerts a force that allows matter to clump together, fostering the birth of galaxies. Without it, the necessary conditions for galaxy formation would not have been met efficiently. Even as galaxies evolve, dark matter remains crucial. It affects the rotation curves of galaxies, an essential feature in understanding their dynamics. The rotation curves of galaxies are graphs that show how stars move at varying distances from the center of the galaxy. Traditional physics tells us that the further a star is from the galactic center, the slower it should orbit. Yet, when we observe real galaxies, the outermost stars are moving far faster than predicted. They orbit at unexpectedly high speeds, which points to the presence of unseen mass surrounding these galaxies. This mysterious mass is none other than dark matter, which, although invisible to the naked eye, makes its presence known through its gravitational influence. In addition to its impact on galactic rotation, dark matter also plays an essential role in the large-scale structure of the universe. It contributes to the formation of the cosmic web, where galaxies and galaxy clusters are strung along filaments of dark matter. These vast, interconnected structures guide the motion and distribution of visible matter across the universe, shaping the cosmos in ways we are only beginning to understand. Dark matter is not a passive bystander. It is an architect of the universe, its gravitational influence molding galaxies and determining their paths through the expanse of time. Over the past few decades, astronomers have developed an impressive array of tools to study the evolution of galaxies. These tools allow us to look back through time and unravel the complex history of how galaxies come into being and change over billions of years. One of the primary methods astronomers use to explore galactic evolution involves observing light emitted from distant galaxies. Since light takes time to travel, this starlight offers a glimpse into galaxies at various stages of their life cycles, revealing how they have evolved. By measuring the redshift of light from these distant galaxies, astronomers can determine how fast the galaxies are receding from us, which in turn reveals critical information about the expansion of the universe. The redshift also provides insights into the age of galaxies, offering a timeline of their development and helping to piece together the broader narrative of cosmic history. In addition to direct observations of light, astronomers rely on advanced computer simulations to model the intricate processes that govern galactic formation and evolution. These simulations involve complex physics to recreate the conditions of the early universe, allowing scientists to visualize how galaxies may evolve over time. The simulations take into account a variety of factors, including gas dynamics, stellar formation, and, of course, the influence of dark matter. By using these models, researchers can gain a better understanding of how the intricate interplay between these elements shapes the structure of galaxies. Another vital tool in this investigation is the study of star populations within galaxies. By examining the light emitted by individual stars, astronomers can determine their age, size, and chemical composition. This information is critical because stars are the fundamental building blocks of galaxies. By analyzing star populations, scientists can trace the history of mass accretion, mergers, and the cycling of matter that ultimately defines the properties of a galaxy. Powerful telescopes such as the Hubble Space Telescope and the James Webb Space Telescope play an indispensable role in these studies. These instruments can capture images and spectra from various wavelengths of light, spanning the near-infrared to ultraviolet regions of the spectrum. This comprehensive range of observations provides astronomers with a more complete understanding of how galaxies evolve. As technology continues to advance, these tools offer increasingly detailed views of distant galaxies, allowing astronomers to unravel the intricate history of cosmic evolution, stretching across vast distances and timescales. One of the most striking features of spiral galaxies, such as our own Milky Way, is their distinctive pinwheel shape. The galactic disk is flat and rotating, filled with stars, gas, and dust. At the center of the galaxy lies a dense bulge of older stars, as well as a supermassive black hole. The spiral arms, which radiate outward from the center, are filled with bright young stars that give them a luminous and vibrant appearance. This spiral structure stands in stark contrast to the more featureless spheroidal shapes of elliptical galaxies. At the heart of a spiral galaxy, the central bulge contains a concentration of older stars and a supermassive black hole, whose gravity affects the dynamics of the entire galaxy. This central black hole can play a key role in regulating the formation of new stars in the galaxy. By pulling in nearby gas and dust, it can affect the supply of material necessary for stellar birth, influencing the overall star formation rate. The disk of a spiral galaxy is a diverse environment, home to stars of all ages. While younger, hotter stars illuminate the arms, older stars provide a contrasting backdrop, contributing cooler, dimmer light. The interstellar medium within the disk, the gas and dust that fills the space between stars, serves as the breeding ground for new stars. These regions of active star formation often appear as bright nebula, contributing to the colorful and dynamic appearance of spiral galaxies. One of the most intriguing aspects of spiral galaxies is their rotation dynamics. Stars and gas in the outskirts of the galaxy appear to rotate at similar speeds to those near the center, a phenomenon that cannot be fully explained by gravity alone. This discrepancy has led scientists to propose the existence of dark matter, an invisible substance that is thought to pervade the galaxy and influence its motion. Dark matter's gravitational effect may explain why the stars on the outer edges of spiral galaxies don't slow down as expected, presenting one of the many mysteries that continue to fascinate astronomers. In contrast to spiral galaxies, elliptical galaxies present a strikingly different form and evolutionary path. These galaxies, which range from nearly spherical to more elongated shapes, lack the well-defined structure of spirals. They do not possess the prominent arms or rotating disks typical of spiral galaxies. Instead, elliptical galaxies are marked by a more homogeneous composition, with little ongoing star formation throughout their lifetimes. Elliptical galaxies primarily grow by merging with smaller galaxies. These mergers can lead to the formation of large, massive galaxies, but they also disrupt the usual star formation processes seen in spiral galaxies. Instead of forming new stars from dense clouds of gas, elliptical galaxies are typically populated by older stars. The gas that would have been used to create new stars is often stripped away during the merger process, resulting in the more subdued color palette seen in elliptical galaxies. A significant feature of elliptical galaxies is the presence of supermassive black holes at their centers. These black holes can be millions or even billions of times the mass of our sun. The energy produced during galactic mergers can fuel intense periods of activity known as quasars, during which gas and dust spiral into the black hole, emitting immense amounts of light. However, as the gas supply is exhausted, this intense activity subsides, further differentiating elliptical galaxies from their spiral counterparts, which continue to form new stars thanks to their ongoing supply of gas. Ultimately, dark matter's influence permeates not just the dynamics of galaxies, but the very fabric of the universe itself. Its gravitational pull plays a pivotal role in shaping the structure of galaxies, guiding their evolution, and helping to define the cosmic landscape we observe today. The environment in which elliptical galaxies exist plays a crucial role in shaping their evolution. These galaxies are often found within dense clusters, where the gravitational pull from neighboring galaxies accelerates their growth and has a significant impact on their dynamic behavior. As galaxies interact with one another, their structures undergo changes, leading to a more complex interplay of stellar populations. This interaction is a driving force behind the emergence of massive elliptical galaxies. Over time, the process of merging, gas dynamics, and the surrounding environmental factors leave an indelible mark on their evolution, making them key figures in the vast cosmic narrative. Elliptical galaxies are particularly fascinating because of their merging history, which can stretch over billions of years, and their response to the gravitational forces of their galactic neighbors. These events are fundamental in understanding how galaxies form, grow, and mature. The gravitational interactions not only shape the structure of the elliptical galaxies, but also influence the types of stars that populate them, the way these stars move within the galaxy, and the overall dynamics of the system. As a result, the galaxies develop a more complex structure over time, filled with multiple generations of stars, as well as varying levels of gas and dust. On the other hand, irregular galaxies offer a stark contrast to their more structured counterparts. These mysterious and chaotic systems captivate astronomers with their unusual, nonconformist shapes. Their irregular forms are often the result of gravitational interactions with neighboring galaxies, or the remnants of smaller galaxies that have merged over time. This turbulent history makes irregular galaxies rich subjects for study, providing a unique window into the processes of galaxy formation and evolution. One of the most intriguing aspects of irregular galaxies is their extraordinarily high rate of star formation. The abundance of gas and dust within these galaxies creates an environment ripe for the creation of new stars. In some cases, irregular galaxies can generate stars at a rate several times greater than that of the Milky Way. This star-forming activity is not only a spectacle, but also offers astronomers valuable insights into the conditions that are necessary for stars to be born. By studying this rapid star formation, scientists can gain a deeper understanding of how galaxies evolve and the factors that contribute to their development. Irregular galaxies are also known for their variety of celestial phenomena. These galaxies often host massive star clusters, remnants of supernova explosions, and even active galactic nuclei, regions at the centers of galaxies that are energetically active. These features provide an exceptional opportunity for scientists to explore fundamental astrophysical processes. Studying the life cycles of stars, the dynamics of gas clouds, and the intricate relationships between star formation and galactic evolution allows astronomers to piece together a more complete picture of how galaxies evolve over time. Perhaps most fascinating of all is the potential that irregular galaxies hold in shedding light on the early universe. Many of these galaxies are thought to resemble the galaxies that existed shortly after the Big Bang, offering a glimpse into the cosmos when it was still young and chaotic. By observing these irregular galaxies, astronomers can explore the conditions of the early universe and gain a better understanding of the processes that shaped the universe we know today. As such, these galaxies serve as an invaluable tool, helping us unlock the mysteries of our cosmic origins. Starbursts, another captivating phenomenon in the life of a galaxy, are periods marked by an extraordinary increase in the rate of star formation. These events occur when vast amounts of gas and dust within a galaxy are compressed, often triggered by interactions with other galaxies or the collision of gas clouds. During a starburst, a galaxy can produce thousands of new stars every year, far surpassing the normal rate of star formation for most galaxies. This surge in stellar creation has profound consequences for the galaxy's evolution. As new stars ignite, they release immense amounts of energy and radiation, which heats up the surrounding gas. This release of energy creates a feedback loop, triggering even more star formation. Over millions of years, this cycle can significantly alter the galaxy's structure and dynamics. One particularly fascinating aspect of starbursts is the formation of massive, short-lived stars. These massive stars burn brightly but live fast, reaching the end of their life cycle quickly. When they do, they explode as supernovae, releasing vast amounts of heavy elements into the surrounding space. This process not only reshapes the galactic environment, but also contributes to the cosmic reservoir of elements that will later form new stars and planets. In summary, the study of elliptical and irregular galaxies, as well as starburst events, offers invaluable insights into the complex processes that govern the formation, evolution, and death of galaxies. These celestial objects, with their rich histories and dynamic interactions, provide a window into the very heart of the universe. By examining them, we can continue to unravel the mysteries of the cosmos and deepen our understanding of the forces that shape the universe. Starbursts are not just temporary flares of activity. They have the power to radically reshape the very structure of a galaxy. As galaxies experience intense starburst episodes, their morphology undergoes significant transformation, often leading them to evolve from graceful spirals into more chaotic, irregular forms. These bursts of star formation, occurring in rapid and unpredictable bursts, can permanently alter the galaxy's characteristics. Over time, such changes can even affect a galaxy's long-term capacity to support life-friendly conditions. The energy released during these explosive periods isn't just confined to the galaxy itself. It can also drive immense outflows of gas, redistributing material across the galaxy and spilling over into the surrounding cosmos. This process not only transforms the galaxy's internal makeup, but also has profound implications for its neighboring galaxies and the broader cosmic landscape. Starbursts are pivotal in the life cycle of galaxies, playing a central role in their evolutionary narratives. By accelerating star formation, they alter the physical structure of galaxies and enrich the interstellar medium with heavier elements, an essential ingredient for planet formation. These vibrant episodes of activity don't merely affect the individual galaxy in question, they ripple through the universe's larger evolutionary process. In this way, starbursts contribute to the broader narrative of the cosmos, shaping galaxies' evolution and affecting the interconnected web of matter and energy that stretches across the universe. At the grandest scale, the universe is structured like a vast interconnected web. This cosmic web is the grand architecture of the universe, a sprawling network of galaxies and galaxy clusters woven together by dark matter and gas. Imagine it as an intricate tapestry, where filaments of galaxies and dark matter stretch across the cosmos, forming a latticework of matter that encircles vast voids of empty space. This network is far from random. Instead, it reveals the underlying order and gravitational forces that govern the large-scale formation and evolution of galaxies. This cosmic web is integral to our understanding of how the universe is organized and continues to evolve, shaping the distribution of galaxies and influencing the formation of new structures. The discovery of this cosmic web was a revolutionary leap in our understanding of the universe, emerging from advancements in observational astronomy in the late 20th century. Early astronomers and cosmologists realized that galaxies weren't scattered randomly across space. Instead, they seemed to follow certain patterns, clustering together in ways that could not be explained by random chance alone. By the 1990s, simulations based on dark matter theories and concepts of cosmic inflation began to bring these patterns into sharper focus, revealing a network of filaments linking galaxies in a giant interconnected web. Large-scale surveys, such as the 2-micron all-sky survey, played a crucial role in confirming the existence of this cosmic web. By mapping the positions of galaxies across vast stretches of space, these surveys provided evidence that galaxies avoid empty regions, instead clustering along narrow filaments of dark matter and gas. This revealed an intricate structure, much like threads in a web, stretching across the universe. Simulations further illustrated how gravity influences the formation of these filaments, guiding galaxies as they form and interact with each other. These findings underscored the vital role dark matter plays in shaping the universe's large-scale structure, serving as a scaffold that directs the formation of galaxies and the evolution of the cosmic web. As our study of the cosmic web deepens, it also advances our understanding of dark matter, the mysterious and invisible substance that pervades the universe. Dark matter is essential in shaping the very fabric of the cosmic web. The ongoing research into this elusive force provides crucial insights into the evolution of the cosmos. Without dark matter, the intricate network of filaments that holds the universe together would collapse, leaving galaxies adrift in empty space. The cosmic web thus represents both a literal and metaphorical structure that helps us understand the deep connections between all parts of the universe. In examining the cosmic web, we begin to grasp how galaxies evolve, merge, and grow over cosmic time. Most galaxies are not evenly distributed across the universe. Instead, they are clustered along the filaments of the cosmic web, creating walls and sheets of galaxies that span enormous distances. Between these structures lie vast voids, almost empty regions where very few galaxies are found. These voids are not merely empty space. They represent the areas of the universe where gravitational forces have had less of an effect, allowing space to expand freely. The cosmic web's delicate balance between the filaments of matter and the voids of emptiness plays a crucial role in guiding galaxy formation and determining the dynamics of the universe's expansion. As dark matter exerts its gravitational pull, it molds the structure of the universe, drawing gas and matter into dense clusters along the filaments of the cosmic web. Over billions of years, these clumps of matter collapse under their own gravity, forming new galaxies. This process enriches the complexity of the cosmic web, adding new layers to its evolving structure. Galaxies born from these filaments grow, interact with one another, and continue to shift the framework of the universe. As these galaxies merge and evolve, they contribute to the ongoing transformation of the cosmic web. The cosmic web study offers profound insights into the larger forces driving cosmic evolution. It helps astronomers decipher the distribution of galaxies and shed light on the properties of dark matter, which continues to elude direct detection. More importantly, it illuminates the broader dynamics of cosmic expansion, giving scientists the tools to predict how the universe will evolve in the future. As telescopes grow more sophisticated and simulations become increasingly advanced, our understanding of the cosmic web deepens, offering a clearer picture of the grand design of the universe and our place within it. To unravel the secrets of the cosmic web, scientists employ a variety of tools and techniques, each providing a unique lens through which we can observe the universe. Telescopes that operate across different wavelengths of light are essential to this process. Optical telescopes, for example, reveal galaxies and star clusters, while radio telescopes detect hydrogen gas, a key marker of matter in the universe. By combining data from these different sources, astronomers can construct a more detailed picture of how galaxies are distributed and how they interact within the cosmic web. Another critical technique is the use of large-scale survey projects, such as the Sloan Digital Sky Survey. These surveys systematically scan vast portions of the sky, cataloging billions of galaxies and other celestial objects. The data gathered from these surveys allows scientists to create three-dimensional maps of the universe, revealing the intricate structure of the cosmic web. By studying these maps, researchers can gain insights into the distribution of galaxies, the role of dark matter, and the ongoing evolution of the universe. In addition to observational data, scientists use computer simulations to model the formation of the cosmic web. These simulations incorporate the laws of physics, including gravity and the behavior of matter, alongside observational data. By simulating the conditions of space, scientists can predict how galaxies and dark matter will behave under various circumstances. These models are invaluable in testing theories about the universe's evolution and in refining our understanding of the forces that govern it. Simulations also provide a framework for comparing observational data, particularly when studying dark matter, which remains one of the universe's greatest mysteries. Gravitational lensing is another powerful tool that astronomers use to map the structure of the cosmic web. This phenomenon occurs when massive objects, such as galaxy clusters, distort the fabric of space-time, bending the light from distant objects behind them. By studying how light is warped on its journey to Earth, scientists can infer the presence of dark matter and map the distribution of galaxies across the cosmic web. Together, these techniques, observational surveys, simulations, and gravitational lensing, allow astronomers to construct a detailed and dynamic representation of the universe's grand architecture. This ongoing exploration helps us unravel the mysteries of cosmic evolution and understand the fundamental forces that govern the cosmos. The universe, vast and seemingly infinite, is not just an empty void. It is intricately woven into a colossal structure known as the cosmic web. This web, composed of galaxies, galaxy clusters, and dark matter, spans the entire cosmos, forming a vast network of filaments that stretch across space. These filaments, connected by vast voids of empty space, form the very fabric of the universe, organizing matter on the grandest scale. The origin of the cosmic web can be traced back to the Big Bang, when the early universe was filled with a nearly uniform distribution of matter. Over billions of years, slight fluctuations in the density of this matter caused it to clump together under the influence of gravity, eventually forming galaxies and clusters of galaxies. As gravity continued to pull matter together, these clumps grew denser, creating the filaments that form the cosmic web. The voids between these filaments are the regions of the universe where matter is less concentrated, creating vast expanses of empty space. This cosmic structure is a delicate balance. The filaments provide paths along which galaxies can move and interact, while the voids allow for the expansion of space. The interplay between these elements has profound consequences for the universe's dynamics. By studying the cosmic web, scientists can gain valuable insights into the distribution of galaxies, the role of dark matter, and the ongoing expansion of the cosmos. Moreover, the cosmic web offers a glimpse into the universe's history and its eventual future, serving as a cosmic map that charts the evolution of galaxies and the destiny of the universe itself. Tiny fluctuations in density across the universe set in motion the cosmic dance of matter, where even the slightest irregularities became the catalysts for the formation of vast cosmic structures. These fluctuations, initially subtle, allowed regions with slightly more mass to attract surrounding matter. As regular matter began to clump together under the relentless force of gravity, dark matter, invisible yet powerful, played a key role. It served as the scaffolding upon which galaxies and even galaxy clusters would eventually form, weaving itself into the very fabric of the cosmos. This gradual process led to the birth of the structures we now call the cosmic web. Imagine this web as a delicate, vast lacework stretching across the universe, composed of thin, intricate filaments of galaxies with enormous voids in between. The dark matter forms the thick threads that interconnect these galaxies, acting like an invisible web, a cosmic glue holding the entire structure together. Meanwhile, as normal matter gathers within these dark matter halos, it begins to cool, condense, and collapse under its own gravity, eventually forming stars and galaxies. Thus, dark matter doesn't just remain an abstract concept. It actively facilitates the accumulation of visible matter, shaping the birth and evolution of cosmic structures. This dynamic interplay between dark matter and visible matter has been pivotal in shaping the universe as we know it today. Understanding how dark matter works not only offers crucial insights into how galaxies were formed, but also illuminates the fundamental processes that dictate the large-scale structure of the universe. The mysteries of dark matter continue to drive much of modern astrophysical research. Even as we uncover more about how it works, the nature of dark matter itself remains one of the great unknowns, pushing scientists to seek a deeper understanding of the forces that govern the cosmos. One of the most captivating aspects of the cosmic web is the formation of galaxy clusters. These clusters are not just random gatherings of stars and galaxies, but act as critical nodes within the cosmic web. A galaxy cluster is a massive concentration of galaxies, dark matter, and gas, bound together by gravity. These clusters form over billions of years, drawn together by their mutual gravitational pull, and often host thousands of galaxies, making them vital hubs of both formation and evolution. The way these clusters form, interact, and evolve provides invaluable clues about the universe's larger structure. Surrounding each galaxy cluster is a complex filamentary structure made up of dark matter and gas, connecting one cluster to another, weaving an intricate network across the cosmos. This structure is akin to a gigantic spider web extending over vast distances, with gravitational forces guiding the movement of galaxies within these filaments. These networks help form the underlying architecture of the universe and give us an image of how galaxies interact within the cosmic landscape. The distribution of galaxy clusters is not random. In fact, by studying the locations and the arrangement of these clusters, astronomers can infer the presence and distribution of dark matter. Areas with a higher concentration of dark matter naturally lead to the formation of more galaxy clusters. This relationship between the concentration of dark matter and galaxy clusters allows scientists to map out large-scale structures of the universe, providing a window into the hidden, unseen forces shaping the cosmos. But the importance of galaxy clusters doesn't end with their role in understanding the universe's structure. These clusters are also places of extraordinary physical phenomena. Many clusters contain hot gas that emits X-rays, offering astronomers a way to study the high-energy processes that occur within. Additionally, the gravitational interactions between galaxies within a cluster can lead to dynamic events such as galaxy mergers. These interactions not only influence the evolution of individual galaxies, but also provide insights into broader cosmological processes, making galaxy clusters crucial laboratories for studying the universe's evolution. The cosmic web itself, sprawling across the universe, is an immensely complex and vast structure that shapes the distribution of galaxies. It consists of three primary components: filaments, nodes, and voids. Filaments are long, thread-like structures where galaxies are densely packed, creating the visible strands of the web. At the intersections of these filaments lie the nodes, the hubs where galaxy clusters form and evolve. In stark contrast to these dense regions are the voids, the enormous, empty spaces between the filaments where galaxies are sparse or non-existent. The gravitational forces within the cosmic web guide galaxies to align along these filaments, shaping them into clusters that can contain hundreds or even thousands of galaxies. Through this intricate network, the universe's large-scale structure begins to make sense. Galaxies do not move randomly through space. Rather, they are shaped by the gravitational pull of dark matter, which guides their motion along these filaments, eventually leading to the formation of massive clusters. This process, unfolding over billions of years, reveals not only the fundamental architecture of the universe, but also the mysterious forces that continue to shape it. The cosmic web, a vast and intricate structure spanning the entire universe, exerts a profound influence on the formation and evolution of galaxies. At the heart of this cosmic network lie the filaments, vast stretches of dark matter and gas that interconnect galaxies across unimaginable distances. Where these filaments converge, the gravitational forces become so intense that they can trigger the collapse of gas clouds, which in turn ignite the creation of new stars and galaxies. These filaments act as both the scaffolding and the conveyor belts of the universe, shaping the very landscapes in which galaxies live and evolve. Within these cosmic networks, galaxies interact and merge, forging new dynamic systems. The gravitational tug-of-war between neighboring galaxies can lead to extraordinary phenomena, such as galaxy collisions or the stripping away of gas, both of which have lasting effects on the galaxy's future development. In essence, the cosmic web is not just a passive backdrop, but a key architect in the grand design of the universe. It dictates not only the locations of galaxies, but also governs their evolutionary paths over billions of years. Its influence extends far beyond mere distribution. It shapes the very processes that drive cosmic evolution. As astronomers peer deeper into these cosmic structures, they gain invaluable insights into the universe's history, unveiling clues about the elusive nature of dark matter and the complex processes that guide the formation of galaxies. The cosmic web stands as a testament to the interconnectedness of all things in the universe. Each galaxy, seemingly an isolated entity, is part of a much larger cosmic tapestry, where every thread plays a crucial role in the ongoing saga of the universe's evolution. At the very beginning of this vast cosmic story stands the Big Bang, the prevailing theory that explains the origin and evolution of the universe. According to this model, about 13.8 billion years ago, the universe began as an incredibly hot and dense point, an infinitesimally small singularity that rapidly expanded in an explosive event. This momentous expansion set into motion the creation of all matter, energy, space, and time as we know it. From this initial burst, the universe has continued to stretch and cool, a process that allowed for the gradual formation of galaxies, stars, and planets. The evidence supporting the Big Bang theory is robust, drawing from several key observations that strengthen its case. One of the most significant pieces of this puzzle is the discovery of cosmic microwave background radiation, CMB, a faint glow that fills the universe. This radiation is the leftover heat from the universe's early days, stretched and cooled over billions of years. It serves as a snapshot of the universe when it was still a hot plasma, providing direct evidence of its hot and dense origins. The uniformity of this radiation across the sky supports the idea that the universe began in a state of great uniformity, which gradually gave rise to the varied structures we observe today. Another compelling piece of evidence is the redshift observed in the light from distant galaxies. As light travels from objects moving away from us, it stretches, shifting towards the red end of the spectrum. This phenomenon, known as the redshift, reveals that galaxies are moving away from us, indicating that the universe is still expanding. Moreover, the farther a galaxy is from us, the faster it appears to be receding. This observable trend aligns perfectly with predictions made by the Big Bang model, reinforcing the idea that the universe has been expanding since its inception. The abundance of light elements in the universe, hydrogen, helium, and lithium, further bolsters the Big Bang theory. According to the model, these elements were created in significant quantities during the first few minutes after the Big Bang, a process known as nucleosynthesis. Observations of the current amounts of these elements closely match predictions made by the Big Bang model, lending further credibility to the theory. Hydrogen, which makes up about 73% of the matter produced at this stage, is the most abundant, followed by helium at around 25%, with traces of lithium and other light elements accounting for the remaining 2%. The presence of these elements, particularly in the proportions predicted by the theory, serves as cornerstone evidence in support of the Big Bang model. In contrast to the creation of light elements, heavier elements like carbon, oxygen, and iron did not emerge in significant quantities during the Big Bang. Instead, they were produced later inside stars through nuclear fusion and during the explosive death throes of stars in supernovae. This process of stellar nucleosynthesis plays a critical role in enriching the universe with the heavier elements that are essential for life as we know it. The Big Bang theory not only accounts for the initial abundance of light elements, but also lays the foundation for the stellar processes that create heavier elements, providing a roadmap for the universe's evolving chemical composition. The earliest moments of the universe, often referred to as the Big Bang, remain shrouded in mystery. The first moments after the event were characterized by an explosive period of rapid expansion known as cosmic inflation. During this brief period, the universe expanded exponentially in a fraction of a second, raising many questions about what triggered this dramatic growth and how it shaped the cosmos we observe today. While the exact mechanisms behind cosmic inflation are still not fully understood, scientists are working tirelessly to unravel the mysteries of this primordial expansion and its lasting effects on the universe's structure. One of the most captivating mysteries that persists in cosmology is the nature of dark matter and dark energy. These two mysterious components together constitute the majority of the universe's mass and energy content. Around 27% is dark matter, while a staggering 70% is dark energy. Yet, despite their profound influence, the exact nature of these substances remains elusive. In the early universe, conditions were so extreme that these exotic forms of matter and energy could have played a crucial role in the formation of the universe's structure. Understanding how dark matter and dark energy interacted during these formative moments may unlock the answers to why galaxies formed in the specific manner that we observe today. As scientists continue to explore these cosmic mysteries, the study of the universe's origins and evolution offers not only answers, but also new questions that challenge our understanding of reality itself. The cosmic web, the Big Bang, and the enigmatic forces of dark matter and dark energy are interconnected threads in the grand narrative of the universe, each contributing to the ongoing story of creation and transformation. At the very core of our understanding of the universe, there lies the concept of the singularity, a point in time where density and gravity become infinite. This moment, thought to have occurred at the beginning of the universe, raises profound and perplexing questions. Singularities challenge the very fabric of physics as we know it, as both quantum mechanics and general relativity falter when attempting to explain what transpired during this earliest phase. The inability to fully describe the conditions of this moment has left a significant intellectual gap in our comprehension of the universe's birth. Some physicists believe that the answer may lie in the development of a theory of quantum gravity, an approach that could potentially merge the principles of quantum mechanics with general relativity. Such a theory might illuminate the fundamental nature of space and time before the Big Bang itself, shedding light on the very fabric of reality during those initial moments. The cosmic microwave background, CMB radiation, offers us a relic of the universe's infancy, a faint echo from its heated state. It serves as a snapshot of the universe as it began to cool and form. However, despite extensive mapping of this radiation, anomalies and fluctuations within it hint at processes that remain largely beyond our grasp. These irregularities might hold crucial clues, potentially offering insights into how matter began to coalesce, leading to the formation of stars and galaxies. As technology advances, so too does our capacity to explore these lingering mysteries, each new discovery providing tantalizing glimpses into the cosmos's first moments. With each breakthrough, our fascination with the universe deepens, revealing complexities that continue to elude full understanding. Cosmic inflation has revolutionized our understanding of the Big Bang, adding new layers of depth and clarity to the original model. Initially, the Big Bang Theory suggested that the universe expanded from a hot, dense state. However, it struggled to explain the uniformity observed in the cosmic microwave background radiation and the large-scale structure of the universe. This is where the concept of inflation steps in. According to inflationary theory, in the moments immediately following the Big Bang, the universe underwent a period of rapid expansion, an expansion so rapid that it stretched space itself at a speed faster than the speed of light. This expansion smoothed out any irregularities in the universe, creating a uniform cosmos that explains why distant regions of the universe, despite being far apart, still have the same temperature. This short but intense burst of growth resolves several lingering questions about the uniformity of the universe and its isotropic nature. Inflation also provides a mechanism for the formation of galaxies and large-scale structures. Tiny fluctuations in the energy density during the inflationary period were stretched across the cosmos, seeding the variations we observe in the distribution of galaxies today. These early fluctuations created the gravitational pull needed to gather matter into clumps, eventually leading to the galaxies, clusters, and other cosmic structures that populate the universe. Beyond improving the Big Bang model, cosmic inflation also connects the early moments of the universe to its current form, offering insights into the relationship between early growth and the present-day structure of the cosmos. This intricate interplay between the universe's early expansion and its later formation enhances our understanding of cosmic evolution, revealing the forces that have shaped the universe over billions of years. While the Big Bang Theory remains the prevailing explanation for the origins of the universe, alternative cosmological models have emerged, each presenting unique perspectives that challenge the foundational tenets of the theory. One such alternative is the steady-state theory, which posits that the universe is eternal, continuously expanding while simultaneously creating new matter. Proponents of this model argue that this process elegantly explains the observed uniformity of the universe without necessitating a singular event of creation. Another alternative comes from cyclic models, which propose that the universe undergoes an endless series of expansions and contractions rather than originating from a singular Big Bang. These models suggest that the universe may evolve through infinite cycles of birth and rebirth, raising profound questions about the nature of time and the ultimate fate of the cosmos. Then there's the multiverse theory, which suggests that our universe is just one of many, each possibly governed by different physical laws and constants. Advocates of this theory argue that many peculiar aspects of our universe, which seem difficult to explain under the Big Bang framework, can be better understood within a broader context that includes multiple universes. This challenges the notion that our cosmos is uniquely significant. The emergence of quantum gravity theories adds another layer of complexity to these alternative models. These theories aim to reconcile the principles of quantum mechanics with general relativity, potentially revealing new insights into the behavior of spacetime that diverge from traditional Big Bang predictions. While these alternative theories provide fascinating perspectives, they also highlight the ongoing journey in cosmology, a quest to refine, expand, or perhaps even redefine our understanding of the universe. Current observational methods continue to rigorously test and challenge the Big Bang paradigm. Astronomers use advanced telescopes to study the cosmic microwave background radiation, a faint afterglow from the Big Bang that provides a window into the universe's early stages. By analyzing the fluctuations in this radiation, scientists gain valuable insights into the distribution of matter and energy in the early cosmos. Although these observations largely support the Big Bang model, they also raise critical questions about the conditions that led to the initial expansion. Galaxy formation and distribution is another area of intense scrutiny. Observations of distant galaxies reveal an unexpected level of structure in the universe, suggesting that galaxies formed earlier than the Big Bang theory initially predicted. This challenges the idea that galaxies formed slowly and gradually and invites further investigation into alternative models, such as the possibility of a rapid period of cosmic inflation. Dark matter and dark energy, too, play crucial roles in these discussions. The Big Bang theory incorporates dark matter to explain the gravitational effects observed in galaxy clusters, yet much about these mysterious substances remains unknown. Theories surrounding dark matter and dark energy are key to bridging gaps in our understanding of the cosmos, and any new insights into their properties could fundamentally change our understanding of the universe's evolution. As we continue to explore these mysteries, our quest to unravel the universe's origins becomes ever more intricate, filled with new theories, observations, and possibilities. The search for answers is far from over, and each step forward brings us closer to understanding the vast, complex cosmos in which we live. However, the true nature of dark matter remains one of the most profound mysteries of modern cosmology. Despite extensive observations, its exact composition and behavior continue to elude scientists, raising the question of whether our entire understanding of the universe's structure and evolution needs a major revision. Similarly, dark energy, the mysterious force accelerating the expansion of the universe, adds another layer of complexity to this cosmic puzzle. As researchers work to refine theoretical models and gather more precise data, these enigmatic components challenge the traditional views of cosmology, prompting a re-examination of the Big Bang paradigm. In each of these areas, dark matter, dark energy, and the Big Bang, scientific progress is not linear. Evolving observations and breakthroughs in technology serve not only to confirm the Big Bang theory, but also to provide new avenues for revising it. As our observational tools become more sophisticated, the universe's intricate and dynamic nature continues to reveal new levels of complexity, urging us to reconsider long-held ideas. This interplay between observation and theory acts as a driving force for advancing our understanding of the cosmos, ensuring that the quest to uncover its origins is far from complete. One of the most significant features in the early universe was the presence of primordial fluctuations, tiny, random variations in density that emerged just moments after the Big Bang. These fluctuations were crucial as they laid the groundwork for the creation of all the cosmic structures we see today: galaxies, stars, and clusters of galaxies. Picture the universe as an immense ocean where tiny ripples on the surface set the stage for the formation of islands and continents. Without these fluctuations, the universe would have remained a homogeneous expanse, a uniform sea of particles devoid of the intricate and diverse structures that make up the cosmos we observe now. The story of these fluctuations began during the inflationary period, which occurred within a fraction of a second after the Big Bang. During this incredibly brief but intense phase, the universe expanded at an exponential rate, far faster than the speed of light. Quantum fluctuations from the microscopic scale were stretched to macroscopic dimensions. These slight variations in density influenced how matter would eventually clump together under the influence of gravity. Regions with slightly higher density would naturally attract more matter, forming the dense clusters we now recognize as galaxies. In contrast, regions of lower density became vast voids. Over billions of years, these early fluctuations evolved, shaping the cosmic fabric and giving rise to the large-scale structure of the universe. As the universe continued to expand and matter clumped together, the primordial fluctuations left behind a lasting imprint on the cosmos. This imprint can still be observed today in the form of the cosmic microwave background, CMB, radiation, a relic from the Big Bang. The CMB offers a snapshot of the universe when it was only about 380,000 years old, revealing subtle patterns that correspond to those early density fluctuations. By studying the CMB, scientists are able to peer back in time, observing the conditions that led to the cosmic structures we now see: galaxies, stars, and clusters. Astrophysicists have spent decades meticulously analyzing the distribution and characteristics of these fluctuations. In doing so, they have uncovered valuable insights into the fundamental forces and the ingredients that shape the universe's evolution. The primordial fluctuations are not merely vestiges of the Big Bang. They are the building blocks of the universe's vast and intricate structure. Understanding them is key to unraveling the universe's trajectory, from its fiery beginnings to the complex cosmic architecture that stretches across billions of light years. Meanwhile, two of the most important pillars of modern physics, quantum mechanics and general relativity, remain at odds when it comes to understanding the universe on both the smallest and largest scales. Quantum mechanics governs the behavior of subatomic particles, describing a probabilistic world where particles exist in multiple states at once, only collapsing into a definite state when observed. General relativity, on the other hand, describes the large-scale structure of the universe, explaining how massive objects like stars, black holes, and galaxies bend the fabric of space and time. This warping of space-time creates what we perceive as gravity. While both theories work beautifully in their respective domains, they are fundamentally incompatible when applied together. The conflict becomes particularly apparent in extreme conditions, such as inside black holes. According to general relativity, a black hole's core collapses to a singularity, an infinitely dense point where gravitational forces are so intense that the laws of physics as we know them break down. At this point, quantum mechanics, with its probabilistic and non-local nature, becomes essential to fully describing the situation. However, reconciling the two frameworks, which operate on vastly different scales and principles, has proven to be one of the most elusive challenges in theoretical physics. This tension between quantum mechanics and general relativity is not just an academic curiosity. It is a key to unlocking some of the universe's most profound mysteries, such as the true nature of black holes, the origin of the Big Bang, and the potential for a unified theory of everything that can explain both the smallest particles and the largest structures in the cosmos. Yet, the task of merging these two pillars into a single, coherent framework remains one of the greatest challenges facing scientists today, and perhaps one of the most important frontiers in the quest to understand the universe at its deepest level. However, quantum mechanics introduces a compelling proposition that challenges one of the most entrenched concepts in modern physics, the idea that information can never be completely erased. This stands in direct opposition to the traditional view of a black hole as an impenetrable singularity, a point where matter and information are lost beyond recovery. This contradiction has birthed one of the most perplexing conundrums in theoretical physics, the black hole information paradox. The paradox has baffled scientists for decades, raising questions about the nature of reality itself and prompting a reconsideration of the fundamental principles governing the universe. In parallel to this cosmic riddle, another unresolved issue looms: the fate of the universe itself. The origins of the universe, specifically within the context of the Big Bang, present a significant point of contention. According to general relativity, the universe began as a singular point and has been expanding ever since. However, quantum mechanics introduces a level of inherent unpredictability into our understanding of the very early universe, suggesting that quantum fluctuations may have been a driving force in the rapid inflationary expansion that occurred immediately after the Big Bang. These fluctuations, though minute, could have had a profound effect on the structure of the cosmos, potentially laying the groundwork for the formation of galaxies, stars, and other cosmic entities. Yet, the true nature of the interaction between quantum mechanics and general relativity in such a highly energetic environment remains a mystery. Despite extensive research, no definitive theory has emerged that can seamlessly unite these two frameworks. This ongoing scientific endeavor has led physicists to explore concepts like quantum gravity and string theory, which aim to provide a unified description of the universe, one that incorporates both the infinitesimal scale of subatomic particles and the vastness of cosmic structures. The quest to reconcile these two competing frameworks is not only intellectually stimulating, but also promises to unlock deeper insights into the very nature of reality. A breakthrough in this area could profoundly alter our understanding of space, time, and the fundamental forces that govern the universe. One of the most captivating aspects of the intersection of quantum mechanics and cosmology is the concept of the quantum vacuum. Traditionally, a vacuum is considered an empty space, devoid of matter. However, in the quantum realm, a vacuum is far from empty. Instead, it is a seething, dynamic field, constantly fluctuating with virtual particles that appear and vanish in a fleeting dance, dictated by the laws of quantum theory. These particles, though momentary, can have significant effects on the physical world, influencing phenomena in ways that are both subtle and profound. In the context of cosmic evolution, the quantum vacuum plays an essential role. Some theories suggest that fluctuations within this vacuum could be responsible for the formation of the universe's larger structures, such as galaxies and galaxy clusters. These quantum fluctuations, which manifest as tiny energy differences in the vacuum, might create minute variations in pressure, ultimately influencing gravitational processes. Over time, these small disturbances could accumulate, leading to the formation of massive cosmic entities. In this way, the quantum vacuum serves as a kind of cosmic backdrop, continually contributing to the unfolding narrative of the universe. Beyond its role in structure formation, the quantum vacuum has far-reaching implications for the very fabric of space and time. Researchers speculate that the energy inherent in the quantum vacuum could be responsible for the accelerated expansion of the universe, a phenomenon observed in recent cosmological studies. This accelerated expansion has led to the hypothesis of dark energy, an unseen force that might be intricately linked to the energy density of the quantum vacuum. This connection raises profound questions about the nature of the universe, challenging our understanding of gravity, the fundamental forces, and the underlying structure of reality. As scientists probe deeper into the mysteries of the quantum vacuum, they gain not only a better understanding of the cosmos, but also a new perspective on existence itself. Each discovery brings us closer to uncovering how this invisible, yet incredibly influential framework shapes the grand narrative of the universe and our place within it. This journey into the heart of quantum phenomena promises to yield insights that extend far beyond the confines of physics, touching on philosophical questions that have long been the domain of human inquiry. The study of quantum mechanics on cosmological scales is an intriguing confluence of two seemingly disparate fields: the minute world of subatomic particles and the vast expanse of the universe. Quantum mechanics typically operates at the scale of individual particles, while cosmology concerns itself with galaxies, dark matter, and the grand structure of the cosmos. Bridging the gap between these two realms presents a significant challenge for scientists, but they are not without tools. One critical method used by researchers involves advanced telescopes and observational instruments capable of detecting ultra-precise signals from distant sources. For example, scientists are now able to detect faint echoes of gravitational waves, ripples in spacetime that are created by events such as black hole mergers. These waves, which are influenced by quantum effects at their origin, offer a unique glimpse into the interplay between the microscopic world and the macroscopic universe. As such, gravitational waves serve as a kind of bridge between the quantum and cosmological realms, revealing how the behavior of the smallest particles can have profound consequences on the largest scales. This research not only advances our understanding of the quantum world, but also provides a powerful tool for unraveling the mysteries of the cosmos. By studying quantum phenomena on cosmological scales, scientists gain insights into the deep connections that bind the very fabric of the universe, revealing how quantum effects shape the structure and evolution of the cosmos itself. Each discovery brings us closer to understanding the complex, interconnected web of reality and our place within it. Experiments conducted at monumental facilities like the Large Hadron Collider serve as a gateway to understanding the earliest moments of the universe. By accelerating particles to staggering speeds and smashing them together with immense energy, scientists recreate conditions that are remarkably similar to those of the primordial cosmos. In these high-energy collisions, researchers probe the fundamental building blocks of matter and the intricate forces that govern their interactions. The results of such experiments could potentially offer us a glimpse into the quantum processes that took place during pivotal cosmic events, such as the Big Bang. In parallel to this, the rapid advancements in quantum technology, especially in areas like quantum computing and quantum sensors, are opening new horizons for understanding the universe on an even more minute scale. These technologies enhance our ability to simulate quantum systems with unprecedented accuracy and measure the tiniest fluctuations in cosmic signals. As researchers continue to challenge the boundaries of what we know, they unveil the mysteries that lie at the intersection of quantum mechanics and the vast scale of the cosmos. This ongoing pursuit of knowledge is not only an exciting testament to human curiosity, but also an unwavering quest to decipher the universe's most profound secrets. Virtual particles, a fascinating aspect of quantum field theory, intrigue both scientists and the general public. Although these particles cannot be directly observed, they provide critical insights into the nature of the cosmos. Essentially, virtual particles are transient fluctuations in energy that occur even in the vacuum of empty space. They appear and disappear so quickly that they remain undetectable by conventional means, but their effects are far from negligible. These brief yet powerful fluctuations play a crucial role in a range of cosmic phenomena. A prime example of their influence is seen in the phenomenon of Hawking radiation, named after the brilliant physicist Stephen Hawking. According to his theoretical prediction, black holes emit radiation as a result of virtual particle pairs forming just outside their event horizon. In this extreme environment, one of the virtual particles can fall into the black hole, while the other escapes into space, allowing the black hole to gradually lose mass over time, a process that could eventually lead to its evaporation. This groundbreaking concept challenges traditional views, revealing that black holes are not truly black, but instead are subject to a slow and gradual process of decay. In addition to their role in black hole physics, virtual particles also contribute to the concept of vacuum energy. Contrary to what we might assume, the vacuum of space is not an empty void, but a bubbling sea of energy where virtual particles are constantly fluctuating in and out of existence. These fluctuations can have significant effects on the fabric of space-time itself, even influencing the expansion of the universe. This connection ties into the mysterious force known as dark energy, which is thought to be responsible for the accelerated expansion of the cosmos. Understanding the relationship between vacuum energy and dark energy is one of the key frontiers in modern physics, pushing the limits of our understanding of the universe. The influence of virtual particles extends even further, playing a critical role in the forces that govern particle interactions, such as electromagnetism and the strong nuclear force. In this context, virtual particles act as messengers, facilitating interactions between particles across vast distances. This aspect of quantum mechanics is foundational not only for high-energy physics experiments, but also for our broader understanding of the interconnectedness of the universe. As scientists continue to explore the elusive world of virtual particles, their findings could unlock additional secrets that bridge the gap between the smallest scales of matter and the largest structures of the cosmos. One of the most mind-boggling phenomena in quantum mechanics is quantum entanglement, a phenomenon that has captivated scientists and lay people alike. Entanglement refers to the deep connection between particles that allows them to influence each other instantaneously, no matter how far apart they are. When two particles become entangled, the state of one particle can instantly determine the state of the other, even if they are separated by vast distances, potentially light years. This seemingly paradoxical relationship challenges our conventional understanding of space and time, offering tantalizing clues about the fundamental structure of the universe. Scientists are increasingly exploring entanglement as a potential key to understanding the deep mysteries of the cosmos. One promising area of research involves examining the behavior of entangled particles under extreme conditions, such as those near black holes or during the high-energy moments of the Big Bang. By investigating how entanglement might influence the nature of space-time in these extreme environments, researchers hope to uncover the underlying principles that govern both gravity and electromagnetism, two of the universe's fundamental forces. Such insights could be critical in unraveling the secrets of the universe's origin, structure, and ultimate fate. As the frontier of quantum research continues to unfold, each breakthrough brings us closer to understanding the interconnectedness of all things, from the minute quantum world to the vast expanses of space. The journey through this mysterious realm is one of both wonder and discovery, as humanity strives to comprehend the forces and phenomena that shape our very existence. Quantum entanglement is not merely a fascinating aspect of quantum mechanics. It holds transformative potential for a wide range of fields, particularly quantum information science. This phenomenon, which allows particles to be interconnected in ways that defy classical understanding, is paving the way for groundbreaking advancements in computing, communication, and cryptography. At the forefront of these innovations are concepts such as quantum teleportation and quantum cryptography, which promise to reshape how we think about and interact with information on a fundamental level. As technology evolves to harness the power of quantum entanglement, the practical applications seem endless. From enabling ultra-secure communication channels to developing machines that operate far beyond the capabilities of classical computers, the possibilities are vast. Yet, these technologies don't merely serve a functional purpose. They also offer profound insights into the fundamental nature of reality. Through entanglement, we are not just crafting better tools, but also peeling back the layers of the universe itself, uncovering the underlying connections that bind all things together. This deepening understanding of nature's most intricate workings could bring us closer to grasping the ultimate mysteries of existence. Quantum entanglement, once considered a curious anomaly, is rapidly evolving into a cornerstone of scientific exploration. As scientists delve deeper into its mysteries, they find themselves standing on the precipice of a new era of knowledge. Every discovery brings us a step closer to unraveling the very fabric of the universe and understanding the interconnectedness of all matter and energy, a concept that we are only beginning to comprehend in its full scope. In parallel with the investigation into quantum entanglement, the exploration of theoretical quantum black holes is igniting excitement in the scientific community. These exotic objects, which lie at the intersection of quantum mechanics and general relativity, offer a potential key to understanding the nature of gravity and the universe itself. Black holes have long been recognized as regions of space where gravity is so intense that not even light can escape. Traditionally, the physics governing these entities is rooted in general relativity, which accurately describes the behavior of massive objects on large scales. However, general relativity fails to account for the quantum effects that dominate at the microscopic level, particularly at the scale of atoms and subatomic particles. Quantum black holes, as hypothesized in advanced theories such as string theory and loop quantum gravity, challenge our traditional understanding of these cosmic phenomena. Rather than being simple points of infinite density as classically understood, these quantum black holes could potentially preserve information about the matter that falls into them, defying the long-held notion that information is lost in a black hole's singularity. This idea resonates with the information paradox, a fundamental question in quantum mechanics that seeks to explain how information is conserved in the universe. By studying these quantum aspects, scientists aim to resolve this paradox and gain a deeper understanding of how the universe processes and stores information. The study of quantum black holes could also bring us closer to unifying the forces of nature, a goal that has eluded physicists for generations. Gravity, described by general relativity and quantum mechanics, which governs the behavior of particles at the smallest scales, have long been thought to be incompatible. However, quantum black holes might provide a bridge between these two seemingly disparate domains, offering new insights into how gravity works on the quantum level. This unification of forces could radically alter our perception of space and time, suggesting that they may not be the smooth, continuous entities we perceive them to be, but instead composed of discrete, quantized units at the smallest scales. While still speculative, the study of quantum black holes represents a bold frontier in physics, one that pushes the boundaries of our current understanding and challenges the very foundation of established theories. Each step forward brings us closer to unraveling the deep secrets of the cosmos, and the journey to comprehend these mysterious objects is just beginning. The intersection of quantum mechanics and gravity offers a rich tapestry of possibilities, not only for the advancement of science, but for the expansion of human knowledge itself. At the crossroads of these scientific endeavors lies the concept of the multiverse, an idea that suggests our universe is just one of potentially infinite others. This thought-provoking theory arises from several prominent frameworks in physics and cosmology, each providing a unique perspective on how multiple universes could emerge. One of the most influential theories is based on cosmic inflation, a period of rapid expansion that occurred immediately following the Big Bang. During this inflationary phase, tiny quantum fluctuations could have given rise to regions of space that expanded in different ways, leading to the formation of separate universes, each governed by its own set of physical laws and constants. In this model, the multiverse is not a singular, unified entity, but rather a vast collection of distinct bubble universes, each occupying its own space while arising from the same overall inflationary event. Another theory, rooted in string theory, offers a different yet equally intriguing take on the multiverse. String theory seeks to reconcile quantum mechanics with general relativity by proposing that fundamental particles are not point-like objects, but rather tiny, vibrating strings. According to this theory, the fabric of spacetime contains additional dimensions beyond the familiar 3 spatial dimensions and 1 temporal dimension. The way these extra dimensions are compactified or curved could lead to the formation of many different universes, each with its own set of physical rules. These universes could differ in their fundamental properties, such as the strength of gravity or the behavior of matter, depending on the specific configuration of these additional dimensions. This idea offers a potential framework for understanding the vast diversity of possible realities that could exist beyond our own universe, each shaped by different conditions and governed by distinct sets of physical laws. The concept of the multiverse invites us to reconsider our place in the cosmos and challenges our understanding of reality itself. It opens up a world of possibilities, suggesting that our universe may be just one small corner of a much larger and more complex multiverse, one in which the boundaries of space, time, and existence are far more fluid and interconnected than we ever imagined. While still speculative, these theories push the frontiers of human knowledge, offering tantalizing glimpses into a reality that extends far beyond what we can currently observe or comprehend. Quantum mechanics, particularly the many worlds interpretation, provides an awe-inspiring viewpoint on the very fabric of reality. According to this perspective, every moment where multiple possible outcomes exist leads to a bifurcation of the universe. At each decision point, no matter how small or seemingly inconsequential, the cosmos splits into numerous branches, each one bringing a different possibility to fruition. In this way, every choice, every event generates a new universe, each unfolding its own unique version of reality. This mind-bending idea invites us to reconsider everything we thought we knew about existence and challenges the very notion of fate, suggesting that all potential outcomes play out in some parallel version of the cosmos. At the heart of this theory lies the concept of the multiverse, an interconnected, sprawling collection of universes, each distinct yet part of a grand cosmic tapestry. These universes, as described by the multiverse theory, are not confined to the same physical laws or constants we experience in our own reality. They may operate under entirely different sets of rules, presenting alternate histories and outcomes for everything from the formation of galaxies to the rise of life. The idea that our universe is just one among an untold number of others offers an entirely new framework for understanding reality, one that fundamentally alters how we think about space, time, and existence itself. This theory, though rooted in physics, reaches beyond science into the realm of philosophy, touching on questions of existence, identity, and consciousness. The notion that alternate versions of ourselves might exist in different universes, each living different lives, making different choices, raises profound questions. If there are infinite versions of us, each pursuing a distinct path, what does that mean for the concept of individuality? What happens to fate or free will in a cosmos where every possible decision is made in some universe? Could our lives be but one branch in an endless forest of possible realities, each one just as real as our own? As outlandish as it may seem, the multiverse theory is not just the stuff of science fiction. There are several scientific frameworks that offer tantalizing evidence in support of this concept. One of the most promising of these is cosmic inflation, a theory that explains the rapid expansion of the universe just after the Big Bang. Some versions of inflationary theory propose that this expansion didn't occur uniformly, meaning that while our observable universe expanded in a certain way, Other regions of space may not have expanded in the same manner. This could have led to the creation of separate pocket or bubble universes, each existing in its own space, with potentially different physical laws and constants. If such inflationary processes can produce separate regions of space, they could also point to the existence of other universes beyond our own, universes that are disconnected from ours, yet coexisting in a vast cosmic landscape. Parallel to this, quantum mechanics offers another piece of the puzzle. The many worlds interpretation of quantum theory suggests that every possible outcome of a quantum event exists in its own distinct universe. This means that every time a quantum event occurs, reality doesn't just resolve into one state. It splits into several, each one representing a different possible outcome. This branching of reality happens on an infinite scale, creating an endless number of universes where every decision and interaction results in a split. Though this remains a topic of debate, both philosophical and scientific, the many worlds interpretation offers a potential framework for understanding how our universe could fit into a much larger multiverse structure. While these ideas remain speculative and largely theoretical, they challenge us to expand our understanding of reality. If the multiverse exists, it might provide answers to questions that have long perplexed scientists and philosophers. Is there a grand design behind the cosmos, or are we simply one version of an endless series of accidents? Could there be other versions of life, other forms of consciousness scattered throughout the multiverse? As we continue to probe the mysteries of quantum mechanics, cosmology, and inflation, we may find that the universe and the multiverse are far stranger, far more intricate than we ever imagined. In the end, the possibility of parallel universes calls into question the very nature of existence. Are we truly masters of our fate, or are we merely one thread in a vast branching tapestry of realities? As we peer into the vast unknown of the cosmos, the multiverse hypothesis urges us to rethink our assumptions about reality and challenges the limits of our knowledge. What lies beyond the boundaries of our observable universe? What other worlds, other lives, other versions of ourselves might be waiting just beyond the horizon of our understanding? The answers, perhaps, are out there, hidden within the boundless expanse of the multiverse. There are, however, indirect but compelling observational hints that could potentially support the multiverse hypothesis. For example, scientists have detected anomalies within the cosmic microwave background radiation, the faint afterglow of the Big Bang. Some researchers interpret these anomalies as possible evidence that our universe might have collided with another universe in the distant past, suggesting the existence of other realms. While these ideas are tantalizing, they remain speculative at this stage and demand more rigorous testing as science progresses. Nevertheless, the mysteries surrounding the multiverse continue to captivate our imagination, pushing the boundaries of our understanding of reality itself. String theory presents a particularly fascinating framework for exploring the fundamental nature of the universe. At its core, string theory proposes that the elementary particles we know, such as electrons and quarks, are not indivisible, point-like objects as traditionally thought. Instead, they are actually tiny, vibrating strings. The frequency at which these strings vibrate determines the type of particle they manifest. This seemingly simple idea has profound implications for our understanding of the universe, particularly when we venture into the possibility of multiple or parallel universes. One of the most intriguing aspects of string theory is its inherent flexibility regarding dimensions. In our everyday experience, we interact with a three-dimensional universe. But string theory suggests that there may be additional, compact dimensions that are not immediately observable. These extra dimensions could influence the properties of particles and lead to variations in the physical laws we experience. In such a framework, entire universes might exist with distinct characteristics, each governed by its own unique set of physical laws. This opens the door to the concept of a vast multiverse, where every universe operates under its own set of rules, potentially with radically different properties. Additionally, there are multiple variations of string theory, each offering its own interpretation of the cosmos. Some branches suggest that our universe could be one of countless others, each emerging at different points in the string universe's evolution. These ideas stem from the concept of brains, which are multi-dimensional objects within string theory. In this context, universes might exist as separate brains within a higher dimensional space. These brains could occasionally interact or even collide, generating new universes in a cosmic web of parallel realities. The theory of the multiverse that arises from string theory is not just a challenge to our understanding of reality, it also ignites the imagination about the very nature of existence. If multiple universes do indeed coexist, it raises profound questions about the laws of physics and our place in this cosmic tableau. Could we be mere observers in a vast landscape filled with alternate realities? The intersection of string theory and the multiverse hypothesis expands the scope of scientific inquiry, pushing the boundaries of what we know and inviting deeper exploration into the very essence of existence. This ongoing inquiry reflects humanity's enduring curiosity and relentless quest for understanding, driven by the limitless possibilities that may await us. The concept of a multiverse also fundamentally reshapes our understanding of time. Time, as we experience it, is typically thought of as a linear progression, past, present, and future. But the multiverse theory challenges this perspective. If multiple universes exist, each one could have its own set of properties that govern the flow of time. Some might experience time as we do, while others might have entirely different temporal mechanics. In one universe, time might be experienced as we know it, flowing in a continuous, predictable manner. However, in another universe, where the laws of physics may vary, the flow of time might be radically different, or even behave unpredictably. One particularly fascinating implication of the multiverse theory is the possibility that time might not be a universal constant. In our universe, time is intricately woven into the fabric of space, creating what we refer to as space-time. However, in alternate universes where the speed of light or fundamental forces might differ, time could behave in ways that diverge significantly from our own understanding. Such variations would offer an entirely new perspective on the nature of time, suggesting that it might not be a fixed and immutable concept, but instead something far more fluid and adaptable, influenced by the specific physical laws of each universe. Moreover, the multiverse theory prompts deeper philosophical questions about the very nature of time itself. Is time a fundamental feature of the universe, an inherent part of reality? Or is it something that emerges from the complex interactions between particles and forces, an artifact of the specific conditions of our universe? In a multiverse where different dimensions and physical laws coexist, time might not be a simple, linear progression, but a malleable and flexible entity, offering new insights into causality, the relationship between events, and the sequence of occurrences. In essence, the multiverse theory and the framework provided by string theory push us to rethink everything we know about the cosmos. They invite us to imagine a reality far beyond the confines of our own universe, where time, space, and the laws of physics can vary dramatically, and where the boundaries of what we understand as existence are stretched to their limits. These ideas spark wonder and curiosity, challenging our perception of the universe and igniting a sense of awe at the vast untapped possibilities that may lie just beyond the horizon of our current understanding. Moreover, each universe could represent a different historical timeline or outcome. Imagine for a moment a scenario where the choices we make at key moments in our lives create branches splitting off into different realities. In such a universe, time would no longer flow in a single unbroken line. Instead, it would become a vast, tangled network of divergent paths, each one corresponding to a different version of events. This idea leads to fascinating philosophical discussions on fate, free will, and how we understand our own existence within this sprawling web of universes. Exploring time in the context of a multiverse challenges not only our grasp of the cosmos, but also invites deep introspection about our place in it. The concept of a multiverse where infinite universes coexist, each with its own distinct set of physical laws and constants, emerges as a compelling extension of the theory of cosmic inflation. Cosmic inflation refers to the period of rapid expansion that the universe underwent in its earliest moments, a phase that set the stage for everything that followed. According to this theory, inflation not only smoothed out the fabric of space-time, but also led to fluctuations in energy density, which eventually gave rise to the formation of galaxies and larger cosmic structures. As scientists delved deeper into the consequences of cosmic inflation, they uncovered the intriguing possibility that it could give birth to a multiverse. In this view, the rapid expansion of space could create pocket or bubble universes, each one with different physical properties. These bubbles could sprout from a common inflating field and grow independently, leading to the birth of a vast collection of universes, each with its own unique set of laws and constants. This suggests that the universe we observe, the one governed by the laws of physics that we know, could merely be one possibility among countless others, shaped by random fluctuations in the inflating field. Moreover, cosmic inflation challenges our very understanding of what is possible. If our universe is just one bubble in a much larger multiverse, then the diversity of cosmic laws across these universes could redefine our most fundamental assumptions about existence. From the nature of life to the very particles that make up matter, everything could vary from one universe to the next. This perspective broadens the scope of scientific inquiry, not only prompting us to understand the workings of our own universe, but also compelling us to consider how different physical conditions could give rise to entirely distinct realities. The idea of the multiverse, therefore, not only expands the canvas upon which cosmologists paint their theories, but it also invites us to reconsider the nature of reality itself. The intersection of cosmic inflation and multiverse theory encourages an open exploration of what lies beyond the confines of our immediate existence, suggesting that the cosmos is far more intricate and complex than we could ever have imagined. As discoveries in this fascinating realm continue to unfold, they promise to stretch the boundaries of our understanding of reality, time, and space. At the heart of multiverse theories lies a set of intriguing philosophical questions that probe the very nature of reality and existence. One such question centers on what it means for something to truly exist. If multiple universes are constantly branching out from one another, how do we define our own reality within the infinite expanse of possibility? This notion forces us to confront the nature of identity and the criteria that grant value to our experiences in a single universe, compared to the countless others that the multiverse theory proposes. Another philosophical implication that emerges from the multiverse is the challenge it presents to our understanding of determinism and free will. In a universe where every possible outcome is realized in a different branch of reality, what does it mean for our choices to matter? This challenges the very foundation of personal agency, suggesting that our actions might not be as consequential as we think, as there are infinite alternate realities where different decisions are made. This perspective raises deep existential questions about fate versus free will, and whether our sense of control over our lives is merely an illusion in a cosmos where every conceivable outcome unfolds somewhere. Furthermore, multiverse theories invite reflection on the very nature of knowledge and scientific inquiry. How can we study or validate the existence of other universes if they lie beyond the limits of our observable horizon? This dilemma pushes us to reconsider the nature of scientific methodology itself and challenges the idea that there is a single unifying theory that can encompass all aspects of existence. It forces us to confront the boundaries of what can be known and challenges the very foundations of empirical evidence. In doing so, it invites a profound reevaluation of the limits of human understanding and the future of scientific exploration. Ultimately, the multiverse not only extends the horizon of our scientific theories, but also compels us to think more deeply about the essence of existence itself. As we continue to explore this concept, it offers a window into the vast complexity of the cosmos and invites us to reimagine the very nature of reality. The ethical implications of multiverse theories provoke deep reflection. If every conceivable version of reality exists simultaneously, does that imply the existence of moral relativism? The notion of divergent universes, where decisions and outcomes can vary dramatically, suggests that ethical landscapes might not be universal, but instead subjective and malleable. This invites us to question the very nature of moral responsibility. How do our choices resonate within the infinite web of possible realities? If we are but one thread in this sprawling tapestry, what does it mean to be accountable for our actions? These philosophical questions not only challenge our ethical frameworks, but also blur the boundaries of science. The multiverse theory extends far beyond physical laws, compelling us to reconsider our place within the universe and our perception of existence. Understanding the complexity of reality through the lens of multiple coexisting worlds offers an unprecedented opportunity to explore humanity's role in a cosmos that could be vastly different from our own. It highlights the importance of considering perspectives from every possible outcome, urging us to navigate a world where the very notion of truth might shift depending on which reality you inhabit. Parallel to these philosophical ponderings is the ever-fascinating idea of time travel, which has captivated the imaginations of scientists, philosophers, and science fiction enthusiasts for generations. Time, an abstract concept we take for granted, has become a subject of intense scrutiny as researchers seek to understand its nature and whether it could ever be manipulated. At the heart of this exploration lies Albert Einstein's theory of relativity, which transformed how we perceive both space and time. According to relativity, time is not an immutable dimension, but one that is inextricably linked to the three spatial dimensions, forming what we call space-time, a four-dimensional fabric. This theory proposes that time can bend and stretch under the influence of gravity and speed. For example, as an object approaches the speed of light, time itself slows down relative to an observer who remains stationary. This remarkable phenomenon, known as time dilation, challenges our basic understanding of time's passage and introduces the tantalizing possibility of time travel. Another concept in theoretical physics that adds a layer of intrigue to the conversation is the idea of wormholes. These hypothetical tunnels in space-time could, in theory, act as shortcuts connecting distant parts of the universe, potentially enabling not just faster travel across vast distances, but also, perhaps, through time itself. Wormholes arise from the equations of general relativity, which suggests that the fabric of space-time can be bent or folded in such a way that one point in space could be connected to another, separated by both time and distance. However, despite their intriguing potential, wormholes remain speculative at best. To function as true time machines, wormholes would need to be stabilized, which, according to current understanding, would require exotic matter with negative energy density, something scientists have yet to discover or fully comprehend. Even if such a substance were found, the technological challenges involved in creating and maintaining a traversable wormhole are enormous. But the very idea of wormholes challenges the limits of our imagination and offers profound insights into the structure of the universe. Quantum mechanics introduces an even more complex layer to the discussion, particularly through its many worlds interpretation. According to this theory, every decision or event spawns a branching of timelines, creating parallel universes where different outcomes play out. This notion raises the possibility that time travel might not follow the linear cause and effect patterns we traditionally expect. Instead of revisiting a fixed moment in time, a time traveler might find themselves transported to an entirely different timeline or reality, where history has unfolded differently. The notion that the past might be altered and that new realities might emerge as a result introduces an exciting complexity to the very concept of time travel. Beyond these theoretical constructs lies the intriguing idea of cosmic strings. These are hypothetical, one-dimensional defects in the fabric of space-time that could, in theory, warp space-time around them. If such strings exist, they could distort the passage of time and even allow for time loops. Theoretically, by moving at high speeds around a cosmic string, one might revisit a moment in the past. While the practical feasibility of such a feat is highly questionable, the very concept opens up new doors for thinking about time and space. Despite the current lack of empirical evidence for any of these theories, they remain compelling in their potential to change how we perceive time, reality, and causality. They stretch the limits of human knowledge, urging us to reconsider fundamental assumptions about the universe and our place within it. While we are still far from achieving time travel or proving the existence of wormholes, The questions raised by these theories push the boundaries of science into uncharted territory, inviting us to explore the mysteries of existence itself. One of the most famous and perplexing paradoxes related to time travel is the grandfather paradox. This scenario imagines a time traveler who journeys into the past with the intent to prevent their grandparents from meeting. If this intervention were successful, the time traveler would never have been born. But if the time traveler was never born, how could they have traveled back in time to prevent the event in the first place? This contradiction strikes at the heart of our understanding of causality and time, suggesting that the very concept of altering the past may be fundamentally flawed. The grandfather paradox is just one of many time travel conundrums that challenge our understanding of reality. Another intriguing example is the predestination paradox, where a time traveler's actions in the past ensure that a historical event occurs as it was meant to. In this scenario, the time traveler becomes a necessary part of history, fulfilling a predetermined role in a closed loop. These paradoxes highlight the complexities of time travel and the philosophical questions they raise about free will, causality, and the nature of time itself continue to intrigue and puzzle both scientists and philosophers. Ultimately, the exploration of time travel, wormholes, and multiverse theories pushes the boundaries of our scientific understanding, urging us to confront questions that have long been relegated to the realm of fiction. While the practical realities of these ideas remain elusive, their philosophical and scientific implications remain profound, challenging our very conceptions of time, space, and the universe. As research in theoretical physics continues to evolve, the allure of time travel and the mysteries of the cosmos remain an open frontier, one that invites us to dream, question, and explore the infinite possibilities of reality. However, by altering the course of events, time travelers might unwittingly become the very catalyst for those same events, creating a paradoxical loop in which the past and future are inextricably linked. This loop disrupts our conventional understanding of cause and effect, challenging our deeply held assumptions about the linear nature of time. At its core, time travel beckons us to rethink the foundations of our reality and invites a cascade of complex ideas about the very structure of the universe. One particularly fascinating theory is the many worlds interpretation of quantum mechanics. This perspective suggests that whenever a decision is made or an event occurs, the universe divides into multiple parallel realities. In this view, if a time traveler were to alter the past, rather than generating a paradox or contradiction, they would merely create a branch into a new timeline, an alternate reality where the events unfold differently. Each of these realities remains valid in its own right, offering a potential resolution to the paradoxes that time travel might provoke. These alternate timelines deepen the ongoing debates about free will, fate, and the far-reaching consequences of our choices, as they transcend the constraints of time. While we have yet to develop the technology to travel through time, these paradoxes provoke rich and thought-provoking discussions about the very nature of time. They compel us to reconsider how time functions and whether our current understanding can truly capture its full essence. In the absence of practical time travel, these intellectual exercises spark our imaginations, fueling both scientific inquiry and philosophical exploration. As we probe these ideas, we edge closer to uncovering the profound mysteries of existence and our place within the cosmos. Time travel has long captured the human imagination. It has become a staple of science fiction, a tantalizing possibility that seems just beyond our reach. Yet it is not merely a flight of fancy. It is a subject that has engaged scientists and philosophers for centuries. At the heart of the concept lies the principle of causality, the idea that every effect has a cause, and that events unfold in a predictable, linear sequence. If time travel were ever to become a reality, it could threaten to unravel this principle, leading to paradoxes like the infamous grandfather paradox, in which a time traveler might unintentionally prevent their own existence by altering past events. To explore the potential of time travel while avoiding the collapse of causality, many scientists turn to theoretical frameworks such as Einstein's theory of relativity. This groundbreaking theory revolutionized our understanding of space and time, revealing that time is not an immutable constant, but a flexible, dynamic aspect of the universe itself. According to relativity, time is intertwined with the fabric of space, creating a unified four-dimensional continuum known as spacetime. Under certain conditions, such as being near a black hole or navigating hypothetical structures like wormholes, it might be possible to travel between different points in time. These extraordinary phenomena could, in theory, allow us to journey through time without violating the fundamental cause and effect relationships that govern our universe. Some researchers have even proposed the existence of closed time-like curves, which are paths through space-time that loop back on themselves, offering the potential to revisit a particular moment in time. These closed curves could provide a way to navigate time without triggering paradoxes. In this scenario, time travel would not involve altering past events, but instead experiencing them from a different vantage point, an observer rather than a participant, without disrupting the course of history. While the notion of revisiting past moments is captivating, it suggests that time travel, in this framework, would not necessarily alter the past, but could offer a new understanding of it. The many worlds interpretation of quantum mechanics also provides an intriguing way to reconcile the paradoxes of time travel. This interpretation posits that the universe constantly splits into multiple branching realities, each representing a different outcome of every possible decision or event. If time travel were possible, a traveler might not change the course of their original timeline, but would instead create an alternate timeline, one that unfolds in parallel with their own. This theory allows time travel to coexist with the causal structure of our universe, avoiding contradictions while suggesting that the universe itself is far more complex and multifaceted than we have yet imagined. Quantum mechanics, the branch of physics that explores the behavior of particles on the atomic and subatomic scale, adds yet another layer of complexity to the conversation about time travel. Unlike classical mechanics, which deals with large objects and predictable motion, quantum mechanics introduces an element of uncertainty and probability. The behavior of quantum particles is governed not by deterministic laws, but by a range of possibilities, each of which could unfold under different circumstances. This probabilistic nature of quantum mechanics raises fascinating questions about the possibility of time travel, particularly when considering phenomena like superposition and entanglement. Superposition refers to the idea that quantum particles can exist in multiple states simultaneously until they are observed. This concept challenges our classical understanding of reality, suggesting that multiple versions of events might coexist at once. In the context of time travel, this could imply that there are parallel timelines, each representing a different outcome of a decision or event, and that it may be possible to travel between them. Some theorists even speculate that time travel might not be about moving through time in the traditional sense, but instead about shifting between different realities that are happening concurrently. Another key principle of quantum mechanics is entanglement, in which two particles become linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. This phenomenon defies our conventional understanding of locality, suggesting that information may not be constrained by the traditional limits of space and time. If time travel were ever to become feasible, it might involve manipulating these quantum entanglements to navigate through time, bypassing the limitations of conventional cause and effect relationships. As we continue to explore the mysteries of time and the possibility of traveling through it, we are confronted with a vast and complex web of theories, paradoxes, and questions that challenge our most basic assumptions about reality. While time travel may remain a distant dream for now, the theoretical exploration of its implications encourages us to think beyond the confines of the known universe and consider the profound complexities of existence itself. However, the implications of quantum mechanics also bring with them a set of paradoxes and challenges. For example, while speculative theories such as wormholes might appear to be theoretically possible, the practicalities of creating and maintaining stable openings for travel through time present obstacles that are, at this moment, beyond our capabilities. While quantum mechanics fuels the imagination and enriches the conversation surrounding time travel, our current understanding still leaves us far from making actual time travel a reality. To conceptualize this, imagine the universe as a vast, intricate fabric, woven together by the threads of space and time. Within this cosmic tapestry, scientists speculate the existence of mysterious structures known as cosmic strings. These hypothetical constructs arise from various theories in physics, particularly those relating to the universe's early moments. Essentially, cosmic strings are thought to be one-dimensional defects in the fabric of space-time itself, born during phase transitions in the cooling process of the early universe. What makes cosmic strings so intriguing is their immense gravitational influence. The gravity they exert can warp the surrounding space-time, creating potential shortcuts or paths that, in theory, could be used for time travel. If two cosmic strings were positioned close enough to each other, their gravitational effects might bend space-time in such a way that traveling along these deformed regions could allow one to move backward or forward through time. Essentially, the intense gravitational pull of these strings could create a time loop, allowing a traveler to return to an earlier point in history. Moreover, some scientists propose that if a spacecraft could maneuver around cosmic strings at a sufficiently high velocity, it might harness this warping of space-time to achieve time travel. This idea echoes Einstein's theory of relativity, which demonstrates that time is not constant, but can be stretched or compressed depending on the speed of travel and the gravitational fields one experiences. Each of these theories challenges our conventional understanding of time and invites us to explore the fascinating, unknown possibilities that may exist beyond the confines of our three-dimensional reality. However, despite the allure of these speculative theories about cosmic strings and their potential to facilitate time travel, it is important to remember that they remain just that, speculative. Cosmic strings have yet to be detected, and there is no empirical evidence to support the ways in which they might enable time travel. This blend of theoretical physics and the unknown continues to spark curiosity, fueling ongoing debates in the scientific community and underscoring our relentless quest to understand the very fabric of the universe. As we peer into the future of the universe, we are confronted with one of the most tantalizing and mysterious questions of all. What is the ultimate fate of the cosmos? Cosmologists have proposed several scenarios, each based on the rate at which the universe is expanding, the density of its matter, and the influence of the mysterious dark energy that permeates space. One of the most widely discussed theories is the Big Freeze. In this scenario, the universe continues expanding indefinitely, causing the gradual cooling of stars and galaxies over billions of years. Stars will burn out and leave behind cold remnants, while matter will slowly drift apart. In the end, the universe would become a dim, dark expanse, filled only with lonely particles, a cold and silent void. Another alternative theory is the Big Crunch. In this scenario, the gravitational forces within the universe might eventually become strong enough to halt the expansion and reverse it, causing all matter to collapse back into an infinitely dense point. This would be a profound return to a state akin to the Big Bang. However, recent observations suggest that dark energy, which accelerates the expansion of the universe, could render this scenario increasingly unlikely. The Big Rip is yet another possibility. This scenario hinges on the assumption that dark energy could become progressively more powerful, eventually tearing apart galaxies, stars, and even atoms. As the universe reaches a critical point, a catastrophic expansion would unmake all structures, leaving nothing intact. Though this concept sounds extreme, it reflects ongoing research into the nature of dark energy and its potential implications for the universe's future. Finally, we cannot ignore the possibility of oscillating or cyclic universes, where the universe undergoes repeated cycles of expansion and contraction. In this theory, after experiencing a big crunch, the universe could potentially trigger another Big Bang, leading to an endless cycle of cosmic rebirth. Each of these hypotheses opens a window into profound questions about the laws of physics and the nature of existence itself, encouraging us to explore the universe's mysteries even further. One particularly fascinating and eerie concept regarding the fate of the universe is the notion of heat death. This theory suggests that the universe will eventually reach a state of maximum entropy, a condition where energy is evenly distributed throughout and there are no temperature differences. In simpler terms, every part of the universe would be at the same temperature, rendering any form of work or energy transfer impossible. It's akin to a battery that has been drained of all its energy. As the universe continues to expand over billions of years, galaxies will drift further apart and stars will burn out. Eventually, all stellar formation will cease, leaving behind remnants such as white dwarfs, neutron stars, and black holes. Over incredibly long timescales, these remnants will fade, leaving a cold, dark universe populated only by radiation and elementary particles. In this bleak landscape, the heat death of the universe signifies a silent, stagnant cosmos, where no reactions can take place, and life as we know it would be impossible. This theory compels us to reflect on our existence in a universe governed by the profound laws of thermodynamics. It serves as a stark reminder of the transient nature of stars and galaxies, and of the ultimate fate that awaits everything we observe. Once a cradle of galaxies and stars, the universe will slowly succumb to uniformity, underscoring the delicate balance of energy, time, and the inevitable march toward entropy. The Big Crunch hypothesis presents a dramatic vision for the ultimate fate of our universe. At its core, this theory suggests that the expansion of the universe, which has been occurring ever since the Big Bang, might one day reverse itself. Imagine a universe that has been expanding outward for billions of years, with galaxies drifting further and further apart, only to be drawn back together by gravitational forces. This hypothesis proposes that all matter and energy in the universe could eventually converge back into an infinitely dense state, returning to the conditions that existed shortly after the Big Bang. In those early days, the universe was an incredibly hot and dense point, and over time, space itself expanded, allowing galaxies to form and stars to ignite. As we contemplate these possibilities, we are reminded of the fragility and impermanence of the universe, its dynamic changes, and the mysteries that continue to captivate the human imagination. However, the concept of the Big Crunch presents a radically different scenario for the universe's future. According to this theory, the universe's current phase of expansion could one day slow down and ultimately reverse, pulling everything back together in a dramatic contraction. This reversal would occur if the gravitational pull of all the matter in the cosmos is strong enough to counteract the force driving the expansion. As this gravitational force gains strength, it could gradually decelerate the outward movement of galaxies, ultimately leading to the universe shrinking instead of growing. Over time, space itself would begin to retract, collapsing galaxies and cosmic structures into tighter and tighter spaces. As this contraction progresses, the temperature of the universe would rise sharply, mirroring the conditions that existed at the beginning of time during the Big Bang. Everything would converge into an extremely dense state, possibly even hotter than before. This immense heat could trigger processes akin to those of the original Big Bang, igniting a cosmic rebirth in reverse. The entire universe, with all its galaxies, stars, and matter, could return to that primordial state, dense, hot, and potentially chaotic, marking a conclusion to the universe as we know it. This dramatic end could signal the closing chapter of time, erasing the universe's present configuration. The implications of the Big Crunch are far-reaching, encouraging profound reflections on time, space, and existence itself. While current astronomical observations suggest that the universe's expansion is accelerating and might continue indefinitely, leading to scenarios like the Big Freeze, the possibility of contraction remains an important counterpoint in understanding cosmic evolution. The idea of the universe winding down and collapsing forces us to confront the ultimate fate of everything, from stars to the very fabric of reality. In contemplating such an eventuality, we not only wrestle with the universe's end, but also with the fundamental nature of time, gravity, and cosmic forces. Consider now a universe driven by an enigmatic force, dark energy. This mysterious force is believed to be responsible for the accelerating expansion of space. In a scenario known as the Big Rip, dark energy's influence could intensify over time, leading to increasingly catastrophic outcomes for the cosmos. As the universe expands at an accelerating rate, Galaxies would eventually be propelled away from one another at faster and faster speeds. This relentless separation would stretch the very fabric of space, causing a gradual rift between galaxies. Over millions and eventually billions of years, this expansion would continue to intensify, tearing apart galaxy clusters and even the galaxies themselves, as the gravitational bonds holding them together weaken under the pressure of the expanding universe. As the Big Rip scenario progresses toward its ultimate culmination, the effects of dark energy would not be confined to galaxies alone. The forces that hold stars, planets, and atoms together would begin to unravel. Stars would be torn apart, planets would disintegrate, and the very atoms comprising matter might break apart. The dissolution of matter itself would culminate in a chaotic end where everything disintegrates into a vast empty ocean of energy, devoid of structure or form. The Big Rip theory raises profound questions about the nature of dark energy and the ultimate fate of the cosmos. It challenges our understanding of fundamental forces and their role in shaping the universe's future. As we continue to explore the mysteries of dark energy, we are confronted with the possibility of a universe where space itself becomes an agent of destruction, tearing apart all forms of matter and energy until nothing remains but the raw fabric of existence itself. This complex interplay between the forces of gravity and dark energy has given astronomers new insights into the universe's expansion. Observations of distant supernovae and the cosmic microwave background radiation have revealed startling clues about the universe's accelerating growth. These findings suggest that dark energy, which accounts for approximately 70% of the universe's total energy, is driving the expansion at an ever-increasing pace. This discovery has reshaped our understanding of gravity and the fundamental forces that govern the cosmos. If dark energy continues to dominate, some scientists speculate that the universe will experience the Big Freeze. This scenario envisions an ever-expanding cosmos where galaxies continue to drift further apart over trillions of years. As stars burn out and galaxies fade into isolation, the universe will grow colder and more desolate. The Big Freeze suggests a universe increasingly devoid of energy, where stars, once sources of light and warmth, will no longer exist. The cosmos will gradually approach a state of darkness and stillness. However, while the Big Freeze seems likely, other theories suggest alternate fates for the universe, such as the Big Crunch or the Big Rip. The Big Crunch imagines a future where gravity eventually overcomes dark energy, halting the expansion of the universe and reversing it into a collapse. In this scenario, everything would be pulled back into a singularity, potentially marking the end of space and time as we know it. The Big Rip, on the other hand, proposes a universe where dark energy becomes increasingly powerful, tearing apart galaxies, stars, and even the fabric of matter itself. Both of these scenarios, though separated by billions of years, offer profound insights into the potential fates of the cosmos. These theoretical scenarios are not merely abstract concepts. Scientists have used advanced telescopes and observational techniques to measure the expansion of the universe, providing tangible evidence for the accelerating expansion. By studying distant supernovae and the cosmic microwave background radiation, astronomers have confirmed that the universe is expanding at an ever-accelerating rate, lending support to the idea of dark energy's profound role in shaping the cosmos. One of the key principles guiding our understanding of the universe's evolution is entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy naturally increases over time, pushing systems toward higher states of disorder. As cosmologists study the universe's long-term evolution, they recognize that the increasing entropy of the cosmos will likely lead to a distant future where the universe reaches a state of maximum disorder, what is known as the heat death of the universe. In this scenario, all stars will burn out and galaxies will drift apart. As the universe expands and cools, energy will be evenly distributed with no significant gradients of temperature or energy to drive processes. With no energy to sustain life or any processes that rely on thermodynamic gradients, all activity in the universe will cease. The heat death marks the universe's final transition into stillness, a state of uniformity and lifelessness, where even the concept of time loses its meaning. the study of entropy has allowed scientists to model and predict the ultimate fate of the universe. By simulating future cosmic conditions, researchers can estimate when stars will burn out, when black holes will evaporate, and when the universe will reach its final, still state. These models provide valuable insights into the long-term future of the cosmos, highlighting the inevitable shift toward ultimate equilibrium. Dark energy, one of the most puzzling and profound components of our universe, challenges much of what we know about cosmology. It accounts for roughly 70% of the universe's total energy density. And unlike ordinary matter, which exerts a gravitational pull, dark energy pushes galaxies apart at an accelerating rate. This repulsive force has led to the discovery that the universe's expansion is not just ongoing, but speeding up. If dark energy continues to dominate the dynamics of the universe, it could lead to a future where galaxies become increasingly isolated, eventually leading to the Big Freeze or even the more dramatic Big Rip. As dark energy grows stronger, the universe would experience a final cataclysmic event, tearing apart not just galaxies and stars, but even the fundamental particles that make up matter itself. The discovery and study of dark energy are crucial in understanding the future of the universe. It challenges scientists to rethink the rules of physics and explore new theories that could explain its mysterious effects. As researchers continue to investigate dark energy's role, it will undoubtedly shape our understanding of the cosmos and the ultimate fate of all that exists.